the button is pressed. Okay, so thank you for coming to the second session. We have a few more talks to go through. And I'm just going to, well, at the beginning, maybe give you a quick recap of the first session of what some interesting talks were. You will get a chance to watch them all again. And I think the video is going to be uploaded in exactly 2 minutes. Okay, so what I like to do at the beginning is a round of introductions. We do have quite a few new people here. And because there are only 24 of us at the moment, I think we actually have time for almost everyone to introduce themselves. So we're gonna go around, and if you want to be introduced, sorry, if you want to introduce yourself, raise your hand in Zoom. Down here, there's a little reactions button with like a little smiley face, and there's a button that says raise your hand. Press that, and I'm going to just call out people one at a time. So quickly, just an introduction for myself. If you don't know who I am, I'm a postdoc here at the University of Western Ontario, and I like meteors. So first one on my list is Peter McKellar. So Peter, go ahead.
Yeah, just got to remember to unmute. I'm not that used to Zoom meetings. Yeah, I'm from Rotorua, New Zealand. Talk about swimming. We've got hot pools, so all year round, nice warm swimming here. So when you live here, you get a bit sick of all that. Yeah, I've got two cameras going, NZ0014 and NZ0017. Been having it going for just over a year now, with the first one anyway. And the group has grown in New Zealand since I've been here, and now we're got about 100 odd cameras, I think, and I've been busy because I've a wee bit more experience than some other people, been busy troubleshooting around the place. So that's where I find my role. But I do scan through all the New Zealand cameras on the site every morning, and just if there's anything exciting there, we can have a look at it a bit further. But we've got a good group going now.
It's an amazing group, Peter. Well, thank you so much. Next up, Rachel. Rachel, go ahead.
Hi, I am Rachel. I'm a postdoc I'm based at Monash University, but I'm also affiliated with Curtin University in Australia. I'm part of the Desert Fireball Network team that tracks meteors coming to Earth. I'm a little bit different in the sense that I'm the geochemist on the team. So I'm not as much focused on the actual fireball, but on the kind of end product of that fireball. So what happens is they track where they go, where they land, we go out and recover them. And then I'm the one who kind of goes through all the data and does the analyses to determine what we've actually got as a rock.
That's amazing. And as far as I understand, you're starting your PhD now at Curtin, right?
Postdoc. So
sorry, postdoc.
Sorry, yeah. So I just started on the 31st of January. So yes, very fresh.
Oh, very awesome. Congratulations. It's a really nice team. You're going to have a great time there. Thank you.
Yeah. I luckily got to do some work with them last year, so it's good to get to know them. They're a great team.
Yeah, they are. Okay, thank you. Next up, Dave Rollinson. Go ahead.
Good morning and good afternoon to people overseas. Yeah, Dave Rollinson, based in Perth, Western Australia. I'm a volunteer at Perth Observatory, and we've got a few cameras around Western Australia. We're able to design the network from scratch, from the ground up. So the layout, we achieved quite a lot with a very small number of cameras. In the past 6 months or so, the network's been expanded by Lexi, who's going to join the call later. We're putting cameras in associated with schools and other institutions, trying to do the STEM and outreach work, and Lexi's going to be on later, and she's done some amazing, really cool stuff. Thank you very much.
Thank you, Dave. Anthony, go ahead.
Hey everyone, I'm Anthony. I'm a PhD student here at Berkeley in the statistics department. So I'm not really a meteor person, but I'm a statistics person who can study that sort of data, and I've worked with satellite-based detections of fireballs, and I'll tell you about that.
Awesome. Thank you so much, Anthony. Peter Jenskins, I see you have yourself unmuted, so if you want to introduce yourself, I mean, do you need an introduction? But go ahead.
I don't know if I need, but it was very nice to see Dave Rollinson in person, as I've been communicating with him for some time. I'm the PI of the CAMS network, and I recovered a couple of meteorites, so you will hear about that shortly.
Oh, you're being very modest, but that's thank you, Peter. We have Ken. Ken, go ahead.
G'day, so I'm north of Perth in Geraldton, and I was part of one of the winning sites to get one of the cameras with the Perth Observatory with Lexi's project. And then I immediately got addicted, so I bought 3 more cameras and set them up. So I'm running 4 now and absolutely loving it.
Awesome, thank you. And from your name, I gather you do astro tours. So can you tell us something about that?
Yeah, so I've been doing amateur astronomy ever since I can remember I can walk, and I do astrotourism predominantly with the Chinese market, and obviously that's slowed down since that virus that ruined everybody's lives, but it's starting to pick up now. But I still do the local market, East Coast, West Coast with astrotourism as well. Yeah, one of my telescopes that I do live astronomy with right there.
Love your background.
Cheers. Yeah, that's all whiskey.
That's awesome. Pete Ashman, go ahead.
Yeah, I'm an amateur astronomer, and I head up the New Mexico Meteor Array in southwestern US. I think we have about 28 cameras now. So I seem to find myself quite busy with meteor cameras pretty much on a daily basis. So it's good to see you all tonight, or today.
Thank you, Pete. And Bob from Cargill, go ahead.
Yes, hi. I'm on the south coast of New Zealand, South Island, and I think there's only 3 cameras further south than me. I have 3 cameras operating. I also look after 3 others in the area. 3 of them not working at the moment, but I hope to get these going. Just a comment, about a week ago, the club rooms where one of our cameras computer is stored was broken into, and I think they tried to pinch the PI, the Raspberry computer, but they must have dropped it on their way out. So we found it lying on the floor with the little chip that plugs in on the other side of the room. So we thought, oh, we're going to have to get another Raspberry Pi computer. But I took it home, connected it all up, and it works fine. So I think those Raspberry Pis are indestructible.
Well, you can push them to a certain limit, but they are built quite well. Thank you, Bob. Next up, we have Jamie Shepherd. Jamie, go ahead. You're still up?
Yeah, it's just gone midnight here in Scotland. Hello, everyone down under. Beautiful, clear moonlit night here. We've got the cameras all running. I started with Global Meteor Network cameras in November 2022. I now have 3 of them. I'm also participating in the UK Meteor Network. And my main love in meteor astronomy has been sticking fisheye lens systems on the roof, which I've been doing since I was a teenager. But this video stuff's got me addicted, and I'm also right into the analysis game. I've dreamed of doing meteor analysis properly for my whole life, I guess. But now with the Western Meteor Pilot tools and RMS and all these things, it's finally become a reality.
Thank you for the kind words, Jamie. Bill Cook, go ahead, Bill. The big boss.
Hi, I'm Bill Cook. I'm the lead for NASA's Meteoroid Environment Office, and we focus on meteors in order to protect our spacecraft and crews. So we have made good use of GMN data in validating our meteor shower forecast and other things. So I'm here just to keep you guys going, so you help NASA protect its vehicles up there. So.
Awesome. Thank you, Bill. We have a few more minutes for introductions. Oh, I see Will Joy. Will, go ahead. Would you mind unmuting? If you don't mind, I'm going to ask you to unmute. There we go.
That might help, definitely.
Awesome. Thank you, Will.
Like Jamie, I'm from Scotland here in Edinburgh. I'm a member of the Astronomical Society of Edinburgh. My passion is meteorite hunting. I've never bought a meteorite, never sold a meteorite, but I found a few. And I've got a camera network sort of in the build, as it were, and I'm hoping to get started on that in the next few months. And it's been fascinating to talk earlier, and I'm going to try and stay up as long as I can before I drop. So if you see me sleeping, then you know why. Thank you. It's nothing to do with the talks. Fantastic.
Awesome. Thank you, Will. We have a few more minutes. Please raise your hand or just unmute yourself, and we want to hear who you are and what you're doing. I see we have a Derek Poulton here. Derek, go ahead.
Yeah, g'day, Dennis. Derek Poulton from Victoria in Australia. So I'm coordinating the GMN network here in Victoria, and we're sort of greatly expanding. We just got some finance to put a nest of cameras at the Leon Moe dark sky site outside Heathcote. We've got some interest from Conniva, which is right across on the South Australian border. So we're gradually expanding. We also collaborate with the DFN Global Fireball Observatory based at Curtin and Monash. And I see Rachel sitting there. Hi, Rachel. We're having great fun and making a lot of interesting sightings. We had a daytime fireball sighting 2 days ago, so that was quite interesting. Enjoying life and gradually expanding the network here and getting a few people involved. So
Awesome. Thank you, Derek. And we have Bob. Bob, I think you're from Texas, right?
Yes, I'm in North Texas, and I've been doing this for a little while, but I got 2 cameras going right now, soon to add 2 more. And a friend of mine, Chuck Goldsmith, is up here too. You've seen him making postings, and we're trying to coordinate our 2 camera locations and observation direction for the camera so we get good cross information.
Awesome. Thank you, Bob. Anyone else? Chuck, Oriane is here. Oriane, go ahead.
Hello again, I'm Oriane. I started with your observations with the French group at Paris Observatory, mainly being involved in the Cabernet and Fripon meteor detection network. Now I'm trying to advertise a lot for the DMN cameras everywhere in the world. And after a few years at London, Ontario, where I had the opportunity to work with Dennis, mainly focusing on meteor stream modeling. Now I moved to Montreal, where I'm the curator of the meteorites collection at the Planetarium de Montréal, but I still have the opportunity of pursuing my research with the Western team.
Awesome. So the message is, if you ever come to Montreal, to go to the planetarium and see Oriane. So that's she's going to show you some cool stuff.
We have like more than 500 meteorites there. You don't believe it, but it's an amazing collection.
That's awesome. Thank you, Oriane. Any last calls? Oh, Lexi is here. I think Lexi should introduce herself. Lexi, if you don't mind. Oh, no. Okay, we're going to wait until the talk then. No worries. Okay, so the next thing that we have on our agenda is a short recap / summary of the first session. And you can watch the video. It is already up on YouTube. But if you don't want to do that, one thing that we can do, well, one thing that I will do is I'm just going to very quickly say what was said in individual talks in the next about 15 minutes. I'm going to really try to keep it short. And I'm just going to go through individual abstracts. And hopefully that might raise some points for discussion later on. We did have a kind of a Q&A / workshop at the end when we discussed a few points. And hopefully we can kind of generate more interest in that. So the first talk of the first session was Paul Rogermans giving us a historical overview of past meteor work. And by historical, I mean literally going back about 300 years before people actually knew that meteors came up from the sky and landed on the ground. And then he gave us a comparison of the performance of different networks compared to the GMN, and showed that the number of orbits and cameras is almost at an unprecedented level. And I got a general feeling that Paul's childhood dream got realized after, after he was able to get involved in this. And he also called for, Paul is running a website called eMeteor News, which is this open journal. And he is inviting everyone, even, amateur astronomers, no matter, it doesn't matter what your level of expertise is. He's interested in having articles and talks about observations of, whatever you're doing. He's interested in having something that can be published in Meteor News to get more people interested in meteor science. Next up, we had an incredible talk by Logan Cordonier, who's from New Mexico, and he is using all-sky cameras to look at persistent trains. Persistent trains occur when meteor blades in the atmosphere, and then there's kind of a little tail, a little bit of an afterglow that can last for several minutes. And using GMN data, he was able to find that actually we can maybe use meteor detections to measure the abundance of ozone in the upper mesosphere. And he's going to push with that work forward. He's doing his PhD at the University of New Mexico, and in the next couple of years, I'm expecting to see more and more interesting things coming from his direction. Next up, we had a talk by Damir Shagon. Was about meteor showers, basically saying that the GMN produces a lot of meteor orbits, meteor radiance, and that it is all fully available on our website. But the issue is that the International Astronomical Union's table of meteor showers is a bit messy, and that needs to be revised, revisited, and we have so much data that we can go in and measure the activity periods, the radiance, the speeds, the orbits of meteor showers, but it's a lot of work. And he's calling for maybe some help, or just kind of people who can help with ideas, or maybe help with some measurements, and maybe hopefully end up with a definition of what is a meteor shower. We will have a talk at the end of this session from Peter Janskens, who wrote a book on the topic, and that's going to be very interesting to hear. Next up, we heard a very interesting talk by Luc Buscan about using meteor cameras, or whatever we develop for RMS, to monitor aircraft and whether or not aircraft produce contrails. And he contributed a lot of improvements to our code. And the idea is that maybe at some point we're going to deploy the software to cameras worldwide and be able to very accurately map track whether or not individual aircraft produce contrails, because contrails contribute 50% of all impact on climate, and global aviation contributes about 3.5% of all of human activity impact on climate itself. So if we could fix a problem of contrails, that is literally a few percent that we can shave off of our impact on the climate. Next up, we have Jamie Shepard. I mean, Jamie's here. You can talk more to him about it, but he actually found a better way of correcting for gravitational bending of fireballs. So if you have a fireball that lasts a long time and it's just kind of skirting the Earth's atmosphere, the Earth's gravity is going to bend its trajectory. And it appears that the method that we used before to correct for that wasn't really working that well. However, Jamie found a new method and a correction to the code that makes it much, much better. And it's kind of happy to hear that we made his, again, dream come true to be able to participate in fireball analysis. And hopefully his months of work might result in some sort of a paper describing the method and showing the comparison of how his method is making fits to fireball trajectories better. And we're all going to get to benefit because our project is open source, and he's going to make his contribution. So yay for open source. Next up, we had Pete Eschman. Again, Pete is here. You can ask him all about it. But we do have a group of people, they're listed right here, who are working hard to make sure that all GMN software is up to date and that the latest operating systems are used. So, if a new Raspberry Pi comes out, like the Raspberry Pi 5, you can download the new SD card image, install it on your Pi, and it's all smooth sailing. There's also an interesting thing that they found is that a Raspberry Pi 5 can run 4 Meteor cameras on same Pi instead of one camera, one Pi, and they're currently developing software to enable that. So this means that hopefully soon we can have almost all sky coverage from one station using just one Pi, which is even a further going to reduce the cost of one monitoring station, which is absolutely incredible. And then we had Mike Mazer. I actually recommend that you definitely go back and watch this talk in the recording because Mike compared different consumer grade sensors that are available on the market right now, which are not too expensive, up to a few hundreds of dollars, and compare their performance paired to different lenses. And he found that with certain combinations of lenses and sensors, you can push the limiting magnitude from, we have now about 6.5 with wide field sensors. If you go a bit narrower, you can push it all the way down to magnitude 11, which is absolutely insane for just a few $100s. Mike is mostly interested in satellites though and space situational awareness, but all this technology is very applicable to meteors as well. Okay, so next up we had Hervé who talked about auroras. So nothing really much to do with meteors, but they are using some methods that we use in the GMN to observe the aurora using 4 cameras that have 4 polarizing filters. And they can actually get the angle of polarization, but they had an issue with image alignment. So they had 4 cameras. Each camera has a different filter. They all observe the same part of the sky, but the problem is each lens has a different distortion, and they have to map each pixel to the exact same coordinate. So they're using the methods that are developed for the GMN and the camera calibration. So I think all of you who are in the camera, you know that the calibration is important. And some of you have used SkyFit, and you know how tricky it is maybe sometimes to get a good calibration. Well, they are using SkyFit, and they applied it to auroral measurements, and they're trying to get some really interesting science out of that. We had a very short talk by Radim talking about our outreach project. So some of you may know, and Lexi is going to say more about it. But Lexi and others are running an outreach program where the idea is to put cameras in schools, give teachers some materials, a curriculum they can use to use with the kids and get kids interested in astronomy, science, computer science, et cetera, et cetera, et cetera. And do it through meteors. I mean, that's how I got started. So for me, meteors are kind of a gateway drug to a lifelong addiction to science. And finally, we had Oriane, who gave us a very comprehensive talk about modeling meteor showers, and that's something that Bill can probably speak more on it, but that's something that space agencies are very interested in, because if you're sending a spacecraft into space or astronauts to space, you want to make sure that there aren't any huge meteor shower outbursts at a time, because that may compromise their safety. And of course, there's some spacecraft that are in space over a long period of time. For example, there's this new giant space telescope with a completely naked mirror. It has a 25 square meters of collecting area. And it's not nice when meteoroids destroy this $10 billion. If meteoroids might destroy, or I guess degrade, the performance of this $10 billion instrument. And Oriane's work has been instrumental, because if you know that a big meteor shower outburst is coming, the satellite can reduce this cross-sectional area, or can turn a hard side towards the radiant, or the important thing is we need to have measurements that inform models, and these models then can make good predictions. And this is one of the big goals of the GMN. Okay, so now, unless there are any questions, I think we can probably start with the first talk of this session. I do see a few items in the chat. Degrade is the better choice of words. Yes, Bill, thank you. Exactly. Degrade a performance, not destroy the instrument. God forbid. Okay, so the first talk that we have is, I think, Rachel. Yeah, it's Rachel. So Rachel, if you don't mind sharing your screen, and go ahead.
Oh, is that looking good?
Looks great. We can hear you, so go ahead.
I'll just move the chat thing out of the way. All right, so yes, as you heard earlier in the introduction, I'm actually a planetary geologist, so a little bit outside of some of the work that you do, but it's all very related. And I will start by showing this image here. So this is the Marili meteorite. So that's the image that was captured on the Desert Fireball network. It came in, I think it was the 27th of November or 2015, 2017. Anyway, and the meteorite itself was collected from Kaditunda, which also known as Lake Eyre, on the 31st of December. So just over a month later, we're able to collect that meteorite. So the Desert Fireball network, some of you are probably quite familiar, some of you might be a bit unknown. We're a multidisciplinary team. So we have a range of people involved, from astronomers, geophysicists, engineers. I'm a geochemist. I have a geology background. And together we all work together to track the fireballs as they come in over Australia, and then with the aim of recovering the meteorites. So this is sort of our setup. We have quite a few cameras out there. There's a few different sort of models that we have. They're often being upgraded, and each station is like that on the left. It's autonomous, and there's a whole lot of software and engineering that goes in so that it doesn't need to have much input from people, which is really useful because they're in very remote locations. But that's able to give us a really good overview of the Australian night sky. They're concentrated in the areas shown kind of on the image on the right there. That's because, for a couple of reasons, those are easier areas that it's easier to then go recover the meteorites from. So because we're really interested in that end stage recovery of the rock, it's important that we're going to be tracking meteorites that fall in relatively more accessible locations. So a lot of the very east coast is quite tricky to find a rock in a fall zone because of the terrain and the vegetation and stuff. So onto the rocks themselves. Meteorites, they sample space, of course. So we have meteorites that come from various planetary bodies. We have some from the moon, some from Mars, some from asteroids such as Vesta, and others that are just kind of really primitive material from the very early stages of the protoplanetary disk that haven't really accreted into any large asteroids. So that kind of initial material from the beginning of the solar system. They're really valuable because they do sample space, and it's very expensive to go and collect material from space. So if we can have the material come to us, that's even better. The other valuable thing about meteorites is that they sample time. So on Earth, the rocks that we have been through a whole lot of geological processes, which means that they've kind of been reworked again and again and again. So we don't actually have samples on the Earth from the very beginning of the solar system. However, meteorites themselves, many of them show that early stage of solar system and planet formation have been disrupted and have just been floating around in space since then. So we have a few that formed within 2 million years of the solar system beginning, so at 4.565 billion years old. And then we have others that are a bit younger. So we have things from Mars that are only about 350 million years old, some that are only 175 million years old from Mars as well. That might sound quite old, talking millions of years, but actually in terms of geology and geological time, that's relatively young. So we're able to get this really great wealth of information. The issue that we have is that that's very decoupled from the geological setting. So on Earth as geologists, when we're getting samples, we generally head out into the field, we understand the geological setting, collect rocks, bring them back and run our analyses. And we kind of use the context of where those rocks came from to develop a picture. It's a little bit trickier with meteorites because it's like someone's brought you an amazing rock collection, but no one has any labels on them. So the context that the Desert Fireball network is able to provide with the orbits and what the rocks were doing prior to their entry into Earth's atmosphere and landing on Earth is really valuable in understanding the formation, the evolution of planets in our solar system. So meteorites hold a range of stories in them. So from the very early stages of the formation of the protoplanetary disk to sort of giant impacts that formed the moon and were sort of really important in forming quite a few of the planets, as well as things like potentially water on Mars and what the climate of some of our neighboring planets used to be like. But of course, these stories need to be read. And that's where people like me come in. So we read them using a whole range of techniques, and I'll run through a few of them now. But I guess it's a lot like a story. So I'm going to tell you today, use an example, a story about a particular meteorite, Miles. And this is just the sort of thing we can do with any meteorite that falls to Earth. So Miles was found in 1992 in open scrubland on a farm in Queensland, Australia, and it's quite a large meteorite. It's 265 kilograms. So for any story, first of all, we need to know who. We do this by using a range of techniques. So one is we can run CT scans, so we can have a look inside the meteorite without actually having to do much to it and damage it. This is a CT scan of Miles where I've kind of removed the metal so that we can look in and see where all the inclusions are in there. We also are able to, one of the main things we do is we slice these open. So we slice open the meteorites and we either produce thin sections or thick sections, which we then look at with optical microscopes, scanning electron microscopes, and a few other techniques to really see what we've got. And that way we can work out who we're dealing with. So in this case, Miles is an iron meteorite. It's got 20% silicate inclusions in it by volume. And the silicate inclusions have a range of mineralogy and chemistry. And they're quite interesting because they're similar to the sort of rocks that we would expect to see from magmas cooled on the Earth crust. That's the inclusions. However, the metal itself is more similar to what we'd expect in sort of a planetary core. So we have this surface material and core material mixed together. So the next question is what? So we've got who, what. So to understand what, we observe the minerals and the textures, and we analyze the chemistry of the different phases. So with meteorites, we can group them. You know, we give each one a name depending on often usually where they're found. And they then form groups. So for iron meteorites, we look at the chemistry of the metal and we look at some particular elements and how they relate to one another. And then we kind of plot them on these diagrams and we're able to determine that Miles is what's called a 2E iron meteorite. It's one of 25 officially recognized. Now, if we're looking at an ordinary chondrite, we use very different sort of classification schemes, but that's all part of the observation and the analyses that we do is to determine what group does this fit in. We can also work out when this happened. So to determine when, we use isotope ratios, and this is able to determine when the meteorite formed, so when it was last kind of at really high temperatures, and that's generally what we call formation, because it's usually sort of a liquid that's crystallizing and forming the rock. So there's different techniques. There's in situ techniques. So we go in and use often either like a laser or an ion beam to zap a crystal, and we look at the ratio of the isotopes that come out of that. So this is what we call a shrimp spot, and that was able to determine the age of Miles. We can also do other techniques like argon, where we kind of extract a crystal and we irradiate it, and then we kind of gradually heat it up and see what isotopes come off, argon isotopes. So from this, we're able to work out that Miles formed 4.542 billion years ago. And this was 25 million years after the first solids in the solar system condensed from the gas. This is actually quite late for meteorite formation. You know, it sounds a long time ago, but a lot of iron meteorites formed within the first 4 or 5 million years. So 25 million years is quite late. We then also know from this that it was heated again. So there was an impact 3.5 billion years ago. So the next question is where? There's two different sort of wheres we can look at. So we can work out where on the parent asteroid did the meteorite form. A lot of iron meteorites have this really interesting texture, which kind of shows that it formed through really slow cooling in the core of a planet. And the ratio of different elements that we analyze within those meteorites also kind of agrees with this assumption. We can also look at things like diffusion profiles. So how do elements change when we kind of go across from one phase to another? We can look at the particular minerals there, because some minerals only form under certain temperature and pressure conditions and under certain cooling rates. And we put all of that together to try and understand where a meteorite formed on the parent body. Was it in the core? Was it at the crust? Was it a big parent body? Was it a small parent body? We can look at all of that through understanding the chemistry and the minerals that we see. The other where is, can we relate this to an asteroid itself? So there's a couple of ways we do that. First of all, we can relate different meteorite groups together. So a good example is the HED meteorites, the Howardites, Eucrites, Diogenites. Together, we've been able to relate them as a single group, and that has then been related to the asteroid Vesta. So by grouping them together, we can kind of build a picture of an entire asteroid, and we can then use spectral observations from spacecraft or even from the Earth to look at the chemistry that we expect to see on these asteroids and then compare it to what we have in our meteorite collection. So for Miles, we've worked out that this actually is interesting for an iron meteorite, most formed in the core, but this one looks like it formed at or near the surface of an asteroid. And it probably formed on the same asteroid as the H chondrites, which is the most common type of meteorite that falls to Earth. And the parent body of these is probably the asteroid 6 Hebe, which is right near one of the Kirkwood gaps. So it's in a really good location for sending off large amounts of material to Earth, because it very quickly falls into one of the resonances with Jupiter that makes these sort of orbits quite unstable, and material is very easily kind of sent into the inner solar system, which is probably why we have a lot of this material in our collection, and we observe a lot of H chondrites falling to Earth. And then we can put it all together. So how did it form? So in the case of Miles meteorite, it looks like it formed in a large impact event at the surface of a parent body. So each meteorite records a chapter in the evolution of our solar system. And the more we read, so the more chapters we read, the more meteorites we read, the more we learn. And we're able to put this together into a global understanding of how our solar system formed, how planetesimals formed, how they evolved through time, the sort of dynamics we had in our solar system as well, what sort of mixing did we have between outer solar system, inner solar system material, and all of that together by looking at these rocks is able to build up that much larger picture. So our story, we start with an asteroid 4.5 billion years ago. And it probably looked a bit like this. This is just a H chondrite, so a metal-rich ordinary chondrite. Then 4.542 billion years ago, so 25 million years after this probably formed, we had a large impact event. And this formed the Miles meteorite. It sat there happily for another billion years. And then there was another impact, probably not quite as large. We don't see overall large scale melting from this impact, but we definitely see heating to at least about 500 degrees. It then floated through space for a while, and eventually it was set onto an orbit that crossed the Earth's orbit and went through space and went through our atmosphere and formed a fireball, which was then picked up by someone and sent to us for research. Now, unfortunately, this was a find, this particular meteorite, so we don't have the orbital data. If we can start tying those orbits to the sort of story that I've presented here, where we'll be able to understand a lot more about the dynamics of the solar system, a bit more clear on where certain parent bodies probably are located, and build up a sort of geological or chemical map of the inner solar system is the aim. So the Desert Fireball Network can really expand this story by involving pre-Earth orbits into all the information that we're able to glean from the rock itself. And that's it. So happy to take any questions.
Amazing. That was very impressive. One of the best put stories that I've ever seen about meteorites. So thank you. Any questions for Rachel? Please just raise your hand or unmute yourself or. Well, I do see a hand up. There's Jesse. Jesse, go ahead.
Hey, it's wondering how many recoveries has the DFN had?
We thought we had 10, but looking at the last one, we've reassessed that down to 9. Actually 8, sorry. There's been a couple. So the tricky thing is, and this is a really important cautionary tale for people who are recovering meteorites, is that we can get these paths, we can get the trajectory, we can get the fall lines. You can go and collect a rock, but that doesn't mean it's your rock. So that's where people like me are really important to come in, because we have the understanding and we have the ability to assess chemically how long that rock has been on the surface. Does it align with the sort of dates we have for the fireball event that we've tracked? And is it actually the rock that we think we saw? We also have quite a few out there that we haven't recovered. Australia's very big. It's really hard to get to some of these places. So in April, we're sending a team out from Monash that to go, and I think a couple from Curtin are probably going to join us, which is fantastic, to the Simpson Desert. So that's a few days drive away through very tricky terrain to recover, hopefully 3 more. So, yeah.
That's awesome. Thank you. We do have another question from Derek. Derek, go ahead. And Bob, if you don't mind, put your question in chat, and then we're going to switch to the next talk. So Derek, go ahead.
Oh, you're muted.
There we go. Is that up? Yep. So how much more valuable? I understand that, we've collected a lot of meteorites over years, but there are very few meteorites where we both have the orbit and have collected the meteorite, Winchcombe or whatever. How much more valuable is it when we have that orbit and trajectory as well as collecting the meteorite?
It certainly is a lot more valuable, but it'll become more valuable the more we do. So in itself, it's interesting, but as we are able to build up this much larger data set, we're going to be able to much better produce sort of these trends and maps and understanding of the inner solar system chemistry and what, like, do ordinary chondrites, do they mostly come from a single sort of pre-Earth orbit? Do we have particular ones coming from Jupiter region orbits? You know, what's the inclination? What's the eccentricity? All that kind of stuff. So in itself, it's interesting, but it's actually the value in having a lot of this data that will really come into sort of a really valuable for science.
Thank you, Rachel. And we're going to go to next talk. Peter Jenskens is going to tell us about a very exciting asteroid and meteorite fall, fireball and a meteorite all in one. So Peter, go ahead.
Let's see if we can figure out how to do this.
One important thing to say is that Australia is probably one of the best places in the world if you want to find meteorites. You're looking for a black rock on a bright orange desert floor. Can't get better than that. It's probably much better than where Peter was searching in Germany a few weeks ago.
Can you see my screen? Oh, all right. Sorry about that. So in this presentation, I'm going to introduce some of these colleagues from Germany, which I now consider my friends because we went to an incredible adventure. You know that in the past, I helped recover the pieces of asteroid 2008 TC3 and 2018 LA, and even last year's fall in France, 2023 CX1. So when this happened again, it was a Saturday afternoon here in California. And I learned about it as soon as the news came. NASA has a system called SCOUT. ESA has its Meerkat asteroid guard system. They both evaluate the first detections of asteroids that are being made to determine whether an asteroid could potentially impact the Earth or could pass us by very closely. Both cases are very interesting. And so in this case, by the time I learned about it, it was about 2 hours after the discovery, and it had already been determined from additional observations that this impact was going to happen in the eastern part of Germany. And that's not far from my parents' home, so I immediately decided that I ought to be going there and bought a ticket. And this asteroid was found by a Hungarian astronomer, Christian Zanecki, at Konkoly Observatory. I don't pronounce his last name correctly. Benz, who gave the talk in the morning session, did a lot better job. But yeah, Christian discovered this object, and he followed it since discovery. So very quickly, a number of observations were being made. This is a nice compilation from Vishnan Observatory. You see the asteroid there move among the stars, and it moves pretty fast. A lot of these detections are, in fact, satellites. So a lot of these early announcements are unreliable, but when it's confirmed that it is actually an asteroid, it's actually on an impact course, that's incredibly exciting. So when that happens, Davide Vanocchia at JPL Caltech provides updated trajectories to get a good idea on where exactly the impact point is expected to be. Initially, that's not so certain. So in our out, it was just eastern part of Germany, but then very quickly it became clear that this was going to be just west of Berlin, and this object was going to impact on a very steep trajectory, and that turned out to be very, very helpful. So then, of course, our cameras are out there. These are the cameras from Mike Henke and Sergio Mola's network, All Sky 7 network in Germany. 4 of the cameras captured the fireball. You see how it brightens and then it breaks, and a lot of fragments were created Pavel Spoonie did a great job in sort of tracking those and figuring out where they should have landed. So I won my ticket. It was an awful ticket. There were 2 red-eye flights with a long 9-hour layover. But fortunately, I could use that layover to look at the 4 locations. That Sunday, people in that area, and those were folks from the Natural History Museum, the Museum für Naturkunde in Berlin, also the DLR, the Deutsches Zentrum für Luft- und Raumfahrt. They are interested in meteorites, they study meteorites, study micrometeorites, and they mobilized and went out. Initially, they looked in the area of Nenhausen, which was where the trajectory came over, where the breaker point was. But in this case, the winds were incredibly important. And initially, the winds we got were from Lindbergh. Sound measurements like these led up twice a day. This one was just half an hour before the impact. You know, and only about 110 kilometers away. So you would think this data is perfect. Turned out not to be so much. But we used this data, me at the airport in Newark. I got confirmation from Rob Madsen. I got confirmation from Dennis Vida, who calculated the Stroon field. And we got confirmation from Pavel Spoonie that, yes, we all agreed this is where meteorites should have fallen. And as you can see, the winds were really dramatic here. I mean, the trajectory is in the top left part of the diagram. Breakup point was about 30 kilometers, but that didn't matter so much. But from that breakup point, everything blew quite a bit southeast and ended up far from the trajectory. So if you look at this graph, you can immediately see some problems. Most of the trajectory is in the forest. You know, problems. And then there was this issue with snow on the ground. So while I was landing in Berlin, I did notice that there was still quite large areas covered in a snow blanket, and that could create problems. So I was picked up by Lutz Hecht and his wife, who were my hosts during the time I was in Berlin. Lutz took charge. He organized the groups from the Museum für Naturkunde and the Freie Universität Berlin, as well as DLR and the Technical University, to join us, to have a group of people that could scour the fields in the hope of finding meteorites. And so we did. Initially went to this little grass field that was in the middle of your graph, searched and all day long and couldn't find anything. That was disappointing. What we were looking for were rocks like this. This was Saint-Pierre-le-Vigier, the one that fell in France a year earlier. A rock covered in some sort of black fusion crust. They sort of sit on top of the vegetation. You know, fairly easily to spot if you're looking for rocks that stand out from the environment. And so you know, that was our target. So then later that night, Pavel Spoonie came with an interesting twist in the story, namely that if you take the wind profile, not from the little balloon, but from wind models, then your whole Stroon field shifts several kilometers further north. And now it puts it just south of the little town of Ribbeck, where there is a castle and a famous gentleman who is mentioned in a poem that the children in Germany know by heart. So it now shifts actually in an area where there's a lot of agricultural fields, and so the such circumstances definitely would improve. Dennis Vida confirmed this, so he actually used a wind profile from a different model provided to him by Adrian Develpois from Curtin, and came up with the same result. Dennis put his meteorites came a little bit more spread out than Pavel, so the exact position for the masses was a little bit different, but as far as where the line was, they now agreed again, like we did before, but now by using different winds approach, we were differently located. So that moved us to Ribbeck. Yeah, here is Lutz Hecht with some people that participate in our search, and Ansgar Kresshake, who is a meteoricist, published extensively on meteorite studies. He's the curator of the meteorite collection at the Museum für Naturkunde in Berlin. So we searched the fields and did our best. We walked all along the line of Pavel and Dennis, and just could not find the meteorite. We did find somebody's hoard of, when the economy collapsed in 1923 in Germany. Somebody buried some coins, and they were scattered in the field, and we found a nice 200 mark piece, a Werthes mark, different type of coins from that hoard. Worth some money, but not what we were looking for. So this was all the areas that we've been searching initially in that central grass field on the southern track, and then later more along Pavel's line, doing vertical scans through the field. We basically walked in the area where the meteorites were on the ground and could not find them. But then on Thursday afternoon, we learned that a Polish team had found a meteorite, and it looked very different than what one would normally expect. It actually looked a lot more like terrestrial rocks. Philippe posted this with his team members in the picture here. And they had looked at the rock for 15 minutes until, they convinced themselves, like, yeah, this has to be a meteorite. It was that difficult. And then next morning, we met up with Philippe, and he showed us the rock. You see here Andrea Mitang and Dominique Dieter from the Vrije Universiteit students looking at it carefully. It was really not the face that was put in the message in the Twitter that was so diagnostic for us, but it was the backside. This was the backside of that rock. And as you can see, if this sits on the ground, you would walk right by it. It was just does not look like a meteorite, even, so from a distance. And so sure enough, after we started searching, it only took an hour or two for Dominique to find one of these meteorites. It was just crazy. Once we knew what to look for, it wasn't difficult. And this was just a strange looking rock. You can see it is covered in fusion crust, but it is sort of translucent. It's translucent on the andesite grains. It has this sort of grayish colored crust at other places, which is a very light gray sort of color, not the black that you would expect from a rock that was rich in iron. And of course, you can say, yeah, but we should have known, because Pavel and Jiri already had determined the day before that these meteorites could indeed be iron poor, because from one of the spectra they took from the fireball, it looked like this was an iron poor meteorite. But we really needed an example to show us. And then, of course, and this is, by the way, is where we found it. We were the first star there at 171 gram. That's the one the Polish meteorite hunters found. I don't know if that position is correct. We're still collecting the data. But we found our 5 gram meteorite quite a ways away, about 4 kilometers. 5 kilometers from where the Polish guys found it. And that basically showed that the line was just fine, that the wind predictions based on the model, not the balloon, but the model, put the strewn field at the correct location. And while we were sort of rambling around and, taking pictures of the rock on the ground and all having big smiles on our faces, I mean, you can see Dominique there being incredibly happy. Kara found another one just 10 meters away, which was incredible. So we had immediately 2 of these meteorites recovered, and we were focusing on smaller ones because we wanted to really sample the variety of materials in the rock. So that evening we found ourselves in the Frau Wechsler Waschhaus Café in Ribbeck, a local cafe where we had an impromptu press conference, and this was the longest press conference I've attended. Questions for about an hour and a half. So it was fun. It was really great to share the excitement with Dominique and Cara. Lutz had a lot to say of the importance of making the find and for the museum collection and for science in general. So yeah, this was exciting. And then, of course, you know, once we were encouraged in finding more meteorites, Robert Luther there found a really big piece, 24 grams. He's part of our organizing team. And Christopher Hamann, who's the lead of our consortium, he found also his own piece. So, you know, we kept finding interesting meteorites. This picture made it into the New York Times. Alessandro brought his whole family along. They searched in our team with the 2 kids, and he managed to find a meteorite. I mean, you know, little rock standing out. So this is the collection from the museum, all the pieces that were collected in the next couple of days. And these are, you know, our first efforts to start analyzing this. So this is Aurélie van den Neuker and Jörn Halbert, both researchers at DLR. And so we've started a consortium study. We've gathered as many people in the community as we can to come up with a good story what this particular meteorite tells us. I hope it's as good a story as Theodore Fontaine's wonderful poem, Herr von Ribbeck auf Ribbeck im Havelland. As I said, it's known by kids in all over Germany, and it's telling the story of a noble gentleman who freely gave his pears from his garden to the kids in the village. But when he passed away and his son was going to take over, he was worried that his son was a little bit more, you know, not as free giving. And so he asked for to be buried with a pear, and the pear grew up from his grave into a nice pear tree, and the kids in the village had their pears ever since. That tree actually existed. It's based on a real story of a gentleman who lived in the late 17th century, early 18th century. It's just lovely. So Ribbeck is famous in Germany, and Ribbeck now is also famous for this really incredible meteorite fall. The 4th recovered fall that we have from an asteroid that was seen coming in space. And as it happens, the 3rd asteroid that is an achondrite. So normally, you know, orbirites only 1 in 1,000. So yeah, incredible adventure. Incredible adventure. Thank you.
Amazing talk, Peter. The story was very well told and incredible. And yeah, the thing about the achondrites, because we know it's an asteroid, we know it's there and it's coming. I wonder the many meteorite falls that we don't find, it's probably because it might be a weird type and we just don't recognize it. And it's probably a big possibility. We are a bit short on time. We are over time, but thank you again. And we can definitely come back to questions later. And Dave Rollinson is here. I think he's eager to talk. So Dave, go ahead.
Thank you very much. Can you see my screen?
Yes, I can. You're good to go.
Awesome. Thank you very much. I'm Dave Rollinson, and I worked on Event Monitor, a feature which was intended to provide fast and comprehensive collation of observations of meteors. It has aspirations to do more, and thank you very much for the invitation to give this talk. And I feel completely awed to be giving this talk surrounded by such experts. I acknowledge the Whadjuk people of the Noongar Nation, on whose lands I am today, and pay my respects to their elders past, present, and emerging. So the objective of Event Monitor is to be able to spot and bring back data from the stations without having to send lots and lots of emails out to people, and try and find operators and get them to send events by emails or provide any desk credentials, because it can take 3 or 4 days to go through that process. Event Monitor automates this, so you can provide a rough idea of what the trajectory is going to be like, and then Event Monitor will publish that to the stations. The stations will send the data back to the server. It does it in a distributed manner. Most of the work, doing the mathematics to work out if the trajectory went through the server, putting together the videos, converting the FF files, the FITS files into JPEGs. That's all done at the station level. So the amount of work that the server has to do is reduced to the minimum. It has to be robust. One of the first rules of the event monitor is don't crash capture. And the second rule is make sure when we're trying to capture an event and bring the data back, that is not a good time to crash. And finally, be selective. Get the data that's needed and as little as possible else. And finally, be nice. I wrote the software, so I've got a good idea how to write a trajectory specification. Other people like Mark and Dennis have done quite a few of these, so they're obviously going to be familiar with it. But the person producing a trajectory, when it really, really counts, might not have done lots of these. And it's possible they're going to be nervous, feel stressed. So it's not at all helpful if it says trajectory invalid, incorrect specification. No matter how little or how much data it's given, it will try and pull out the right trajectories and the right images and the right bits of data so that when it all gets back to someone who can do a reduction, they can try and form try and do the maths. The layout of Event Monitor was set out quite early in the piece. Dennis sort of came out with a rough architecture of it, and it got very, very slightly refined. But as it is today, it's not changed very much. So up at the server, all we have is a text file, which is the watchlist file that some people might have seen. That goes into the web server, the same web server, I think, that serves all the pages of the Global Meteor Network website. It goes down to stations. The stations run it through a parser, which I call a kind parser, because it tries not to be too syntactically nitpicky. If it can make some sense of what it's been given, it will try and return the events. That goes through a function called getEvents, which looks in the captured files directory. That all ends up in an SQLite database, which I'll say a little bit more later. Works out if it went through the field of view of the camera. If it did, send it, and it goes back up to Canada. So it's not really the world's most complicated piece of architecture. And that was a really good idea because keeping things simple gives them a pretty good chance of working. And that applies in most things I've ever been involved in my life. And we definitely took a decision to make it simple. And using a well-established database package to hold all the data for the trajectories we were trying to recover was really a good idea as well, because there's 3 or 4 different tools that let you look at an SQLite database, and you can see what Event Monitor is trying to do, and that really helped the debugging processes. But in order to recover the trajectories, we had to write a very simple language to allow us to specify it, and I've called that M because I wanted to give it a name. And it looks a bit like the kind of thing you might find in a Linux config file. That was very deliberate. We wanted it to look familiar to people who are used to working with Linux and even Windows INI files. There's various keywords on the left-hand side. And if you want to recover some data, if you give it an event time, a latitude, and a longitude, that's all you need. It will try and do best guesses for everything else. Obviously, the more data you can give it, the more chance you will have of getting the right data, and the smaller the amount of data that will get returned. But the decision to make it as easy as possible to get something back as quickly as possible was very, very important. And other people who've used it have said to me that they upload the event specification, and within minutes, data starts to arrive. One really cool feature is if we know when an event is going to happen, you can put in a future event. An Event Monitor will wait until the instant, it waits until about 10 seconds after the event, and then starts to run through the process of finding the data in the captured files directory, working out if it went through the field of view, and then tries to send all the data back. There is a risk that it's going to sort of flood the server with a lot of data, especially over the UK. So there's quite a lot of work gone into backing off and seeing if the server's too busy to receive the data. Just a little bit on the mathematics, because this is a really, really simple looking piece of vector mathematics that just does something so powerful. One of the first checks that the Event Monitor does is say, do I have data for this time? If it does have data for this time, then it works out if the station is within a certain radius of the trajectory. And it is the radius of the trajectory, not the trajectory projected on the ground. So anything that's less than 30 kilometers away probably won't activate a station at all. because the trajectory generally stops more than 30 kilometers above the ground. So if you imagine a circle that's tiny, put it around the station, and then you grow and you grow and you grow that circle until it just touches the trajectory. The trajectory is now a tangent to that circle. And the radius from the station up the trajectory is perpendicular to the trajectory. And that's a really, really important point, because that makes the next stage that is almost magical possible to do. So the next stage is to work out where that closest approach point is. Now we know where the station is, and we invented a start point for the trajectory. Once we know that, we can do what's called a projection of this vector, which is from the station to the start point, onto the trajectory that we've imagined. And to do that, if you imagine a point source of light infinitely far away down here, shining onto this vector, the shadow it casts onto the trajectory is the length of the projection. The reason why that's useful, and the reason why that right angle is so important, is that if we go backwards along this trajectory, use backwards along this vector, use the direction of the trajectory and this length, it finds the exact location of the closest approach to the trajectory to the station. Once we know that, we can say, is it even worth looking at this trajectory in any more detail, or is it just too far away to be worth bothering with? And to show the beauty of that piece of mathematics, that's a line of code that does it. So vector mass, taking the dot of two vectors or the projection, is an incredibly powerful technique. And if there was a heart of the whole event monitor project, it's that line of code. There's other ways to do it. Iteration, which might blow up your code, calculus, which might blow up your house, and trigonometry, which might blow up everything, because arctans tend to get a bit picky about what you feed them. But vector mass is really, really cool, very accurate, and really simple to implement. And then finally, did it pass through the field of view? I tried to do this again using vector mass because I felt I was on a roll. I wrote 2,000 lines of code that was incomprehensible and didn't work. So Dennis said, look, just cool your jets, mate. So to do that, we find the start point of the trajectory and the end point, iterate along it. And if any point appears in the diagonal field of view, then report it as a trajectory that the camera has seen, and upload the files. There's some future work in the pipeline. So only when there's a contemporary FR file or a fireball report that's implemented and working now, we can look at various RADEC points on the sky and pick those points in history. The code's written, it's been used for real once. I don't know if Dennis has announced what we've done. Hopefully he will at some point. Some work to monitor satellites using TLEs. It's kind of a victim of its own success because it generates far too much data, and it actually prevented me from downloading something that I needed to get one night, because I think the ISS and that Blue Walker satellite had been through, and it just created so much data that it prevented me from downloading what I needed. So I've parked that for a while. Specified by unique trajectory identifier, and there is the very first one in the GMN database. Distributed fireball discrimination, trajectory specification and retrieval. Use these stations to try and work out if there was a fireball by looking at the pattern of stations which saw it, or saw a bright event, and work out if that fits in with a library of trajectory specifications in the database. And finally, a point that I've just added in is maybe see if we can tie in recovery of radiosonde data to specific events that Event Monitor has been notified of. Thanks very much for the opportunity to give the talk, and to Dennis and Mark for trusting me to write this feature, the operators who risk their sanity allowing me to test Event Monitor, and for all the participants in this amazing research project. Good morning. Thank you.
Awesome. Thank you, Dave. Just for context for a lot of people, in the first session, I said that due to diplomatic reasons, the GMN does not have very strong fireball integration, central integration. But what we are trying to do is making sure that people who run their regional networks can get easy access to their data. And what Dave is doing is exactly that. People can very easily now reasonably easily go in, specify whatever the firewall or an event they're looking for, and data is going to be collected on their user directories and their cameras that can be collected, and they can do whatever they want with it then. And hopefully one day we can extend these features to, for example, if we had, let's say, a firewall observed with the GLM, we could automatically trigger event monitor, and with other source of information, we could automatically pipe it in, and all that data is going to be extracted and saved, and good stuff can be done then. Thank you, Dave. Are there any quick questions for Dave? I'm actually thinking about the next 5 minutes. We are a bit over time. Next 5 minutes to be kind of a break / question period. So let's take 5 minutes for a break / question. I see Jamie has a question. So Jamie, go ahead.
Just a comment, David, we've used your event monitor here in the UK for rapid gathering of lots of data files on some bright fireballs, and it's been very successful. It's just amazing. You get this huge file of data, and you can get into the analysis within a few hours of the event. It's especially important, though, because often an event is captured but not detected by RMS. And some of these Raspberry Pis are so full of files that they only keep the captured folder for possibly as little as one night. And there's been more than once where the event monitor has saved data from oblivion. So thank you.
Oh, well, thanks very much. It's great that to meet people using the stuff that I wrote. Yeah, it's phenomenal, and I'm very proud of the way it's being used, and I'm very proud of the way it's working. You know, it's doing what it needs to do. So thanks so much for the feedback.
Awesome, thanks, Dave. Bill Cook has a question. Bill, go ahead.
Yeah, forgive me for being confused. Does Event Monitor execute on the GMN server or locally?
It runs at the station. All the work is done, is distributed to the edge of the network. That was a deliberate choice early on, which put some pretty terrifying work onto me, but you know, I kind of just went forward with it.
Excellent, thank you.
Yeah, so the GMN server just hosts a file that's publicly available on the website that says, this is kind of what we want data for. And then it goes in and extracts everything and uploads it to user directories where they can access the data. And of course, it can be collected that way. That's one thing that we, how can I put it? We want to give access to this to regional coordinators, and right now has been kind of limited to a beta tester group. So if, you know, there's a regional coordinator who doesn't have access to this, please talk to us, and then we'll work something out. Okay, are there any more questions for any previous talks for either Rachel or Peter Jenskens about the meteorite fall? Just please go ahead and raise your hand. If not, feel free to take a break until, let's see, we start 17, about 3 more minutes. Let's wait 3 more minutes so people can go and do whatever they need, and I'm going to take those 3 minutes. So I'm just gonna leave the meeting open, and I'll be back in 3 minutes.
Hi, David. Derek here.
Hey, Derek, how are you going?
Oh, good, thanks, mate. Oh, just very interesting talk. I was
Thanks.
just fascinated by all that. Because we're working with DFN, Hadrian's saying he wants an ESCV file. I wonder that we can then use to correlate with any DFN events. Does the event monitor capture something like that? Yeah.
It doesn't. It doesn't. The ESCV file, I think, has to be generated by someone doing some actual work.
Yeah.
That's the output of what Event Monitor will collect for you. So you get that data in, you do some work in SkyFit, and the SCV file comes up kind of out of my boundary area. So if anyone else is on the call and wants to correct me, please go for it.
I mean, I had a look. I understand how you can use SkyFit to generate, Dennis's tutorial goes through that, how you generate the EC SV file once you have a couple of stations with trajectories.
Yeah.
But yeah. So there's a bit of hard work you need to do, basically. Yeah.
I can't. All Event Monitor is a crafty way of retrieving the data. Rather than, I mean, I think, about a year ago, you were trying to get hold of the rocket body data, and it was sat on someone's Pi, and they were away, and we were just working out when it was going to get overwritten, and we knew we had no chance of recovering it.
Yeah.
And the really annoying thing was I was about 3 weeks away from being able to roll Event Monitor out, but you can't rush these things.
Is Nick Moskovitz one of your beta testers?
Could well be.
Check if he is, because we had a Meteor 4 last December and want to make sure that all the data were recovered from that.
Yep. I don't think last December it would have. Oh yeah, last December. Yep, it would have been in use. So many people use the software now that I don't know who's creating trajectories.
Awesome. So I just got in. Sorry, were you chatting about the Arizona Fireball or?
I was, but yeah.
Yeah. So Event Monitor was used for that, and then we realized that we only got a very short beginning and couldn't really tell and nothing much about the Fireball. But
so we have 2 detections with TFN. So with that short piece added to it, and Mike Henke has it on several cameras. I think all in all, we just have to combine all the resources. We're gonna have a good trajectory on this one.
Yeah, good, cool. Okay, I think we can go with the next talk. So Anthony, are you ready?
Yep, just a sec.
Awesome, thank you. Go ahead.
Share screen. Okay, can you all see something that looks like a slide?
Looking good.
Great. Okay. Yeah, so hi everyone. I'm Anthony, again, statistics department at Berkeley. Not a Meteor person, but I've worked with data relating to bolides, specifically from the GOES GLM satellite. And today we're going to talk about that satellite and how to work with that data. So we're going to start with, what is GOES GLM? What does it do? Next, we're going to talk about like some issues when you try to statistically analyze their population of bolide detections. Next, the light curves from GLM aren't quite right in the raw data. So there's some technicalities about calibrating them. Finally, we're going to get into some research results, new directions and things, and then do a little bit of a software demo. Okay, so what is GOES GLM? So it's a lighting instrument that's on a weather satellite, a NOAA weather satellite, which is not designed to detect bolides, but it does detect bolides. GOES is Geostationary Operational Environmental Satellite. GLM is Geostationary Lightning Mapper, which is an acronym that is annoyingly close to GMN and also Generalized Linear Models as a statistician. Okay, so more GLM pictures. That's what it looks like without the sun shield. That's what the satellite looks like. There are kind of 2 GLMs operating right now. One in the GOES west position, one in the GOES east position, and gives you a pretty big field of view, something like, I don't know, 45% of Earth coverage, and a nice stereo region where there's overlap and you can detect events with 2 satellites at the same time. Now this is kind of like a weird field of view shape. It's not that weird from GLM's perspective. It's a square with the corners cut off. And yeah, a lot of different bolide detections. So a little bit about the sensor. It's a CCD with a narrowband filter about 1 nanometer at the 777.4 nanometer oxygen line. Runs at 500 hertz, which is pretty fast. But spatially, it has like a relatively low resolution. If you project the pixels onto the surface of the Earth, they're about like somewhere 8 to 14 kilometers big, depending on where on the Earth you are. Nice thing though, the data is streamed from the satellite in real time, and NOAA processes the data all in real time. And so that's a sensor. So Jeff Smith and other people at the SETI Institute have developed a automated detection pipeline, which turns the detections that GLM makes, which are mostly lightning, into bolide detections, because some of those are actually not lightning detections, they're false positives for lightning, but true positives for bolides. And so what the pipeline does is it basically just clusters lightning events, and then does some machine learning with a random forest, now a convolutional neural network, pulling in GLM data and some other data sources from other instruments on the satellite, to basically look at, okay, does this look like previous bolides? And the accuracy that it classifies started to get shockingly high because of the large amount of training data. And so to date, there have been 6,719 bolide detections published, all human vetted. A lot of them are stereo detections, so detected by 2 satellites. We get pretty nice detailed light curves. Here's an example. Also in the stereo region, it can sometimes traverse enough pixels that you are actually able to estimate trajectories just using GLM. And some other key points, GLM can detect in all weather conditions, rain or shine, night or dark. It works pretty well. And so it can be pretty tempting to jump into using this data in some sort of statistical analysis, but we need to be really, really careful with that, because GLM is not designed to detect bolides. So first of all, the data products. NOAA puts out level 2 and level 0 data. Level 2 data is the most highly processed data, and it's currently used for the bolide detection pipeline, and the bolide data that gets published here comes from the level 2 NOAA data. There's also level 0 data, which is the unprocessed pixel level data, and this is currently what's used for correcting light curves. Yeah, it's interesting that all of NOAA's processing is designed for lightning, right? And so sometimes things get messed up in the data, and then we have to reverse engineer certain things to make it work for bolides. Now the Asteroid Threat Assessment Project team, which is at NASA Ames, has this website, neobolide.ndc.nasa.gov, where all human vetted data detections, human vetted bolide detections are published, and there's some human annotation, some nice things there. There's also a lot of output from the detection pipeline, vetted, unvetted data, a lot of different details. You can get calibrated light curves, and there's much more to come in the future. Okay, so now about the difficulties of analyzing GLM's bolide detections. So first of all, the field of view. Now, the nominal field of view is not actually the field of view of GLM for reasons that I'm not party to. And in particular for GOES 17, there were yaw flips that changed the field of view, and this is just something to be careful about if you're analyzing, how many bolides are we seeing? You have to be careful about the size of the field of view, and precise data is available in the Python package that we have called bolides. Next, in the human vetted data in particular, there's a strong detection bias towards the stereo region, because as a human, if you see a double detection, you'll obviously be much more confident in that being a true bolide. And so this causes kind of an increase in detection efficiency in the stereo region, which you can measure at about 1.4 through some modeling. And then there are interesting questions about how do you treat double detections, that one detection or 2 independent detections. Yeah, just something to be careful with when you're doing statistics. Next, the incidence angle. So the satellite has a narrowband filter, and the angle of incidence is this angle here, kind of, from sort of the angle that it's entering the sensor at. And because it's a narrowband filter, as that angle changes, the effective sort of bandpass of the filter shifts as well. And that can start, as you move far away, that can start moving you out of the oxygen triplet region, and you really start losing a lot of light. And so this is some data about the filter transmittance, and you can see that it kind of really starts to drop off as you get to high angles of incidence. And it actually was designed to peak at about 5 degrees angle of incidence. And this actually shows up in the bolide detections, where through some complicated statistics and modeling, you can see that bolide detections actually seem to peak at about 5 degrees, and they drop off further away from the nadir of the satellite, and also drop off right at the nadir as well, because it's designed to peak at 5 degrees. Next, complicated detection bias that can also be modeled. there are different kinds of background that you can have. You can have detections over land, you can have detections in places with lots of lightning, and detections in very cloudy places. And this affects how bright the background is, and also possibly interacts with how the classifier works as well. And so these can all be modeled, and it seems that the detection efficiency is lower in places with a lot of lightning, is lower in places that are over land, and also is lower in cloudy places as well. So just some things to be careful about, and this also requires, I think, some more study and modeling. Now, really, the key thing to be careful with is velocity, because GLM detects at the 777 nanometer line. It really is sensitive to high velocity objects, because within that band, the oxygen line emissions increase much faster than continuum radiation as velocity increases, which leads to interesting things like for oh, sorry, these should be flipped, I think. That's my bad. Oh no, sorry, that's fine. It shouldn't be flipped. At high velocities, GLM is able to detect far dimmer objects in terms of visual magnitude than objects that are at low velocities. So at 50 kilometers per second, the limiting magnitude is about -14 visual magnitude, and at 70 kilometers per second, it's about -9 visual magnitude. And this is not something that was really anticipated beforehand, and it really changes what population of objects you end up seeing in the data. And this paper here has a treatment of this topic. You can see, for example, that really fast meteor showers like the Leonids and Perseids and Eta Aquariids really show up in the data, whereas other meteor showers do not show up at all. Or, I mean, they show up a little bit, but basically nothing compared to the Leonids. And that is partly, I think, due to this bias due to velocity. Here as well, the diurnal variation has a very strong peak at 6 in the morning, which is consistent with it having a strong apex source and hence, very high velocity meteors. This histogram here is bolides from GLM, peaks at 6 in the morning. Bolides from USG, the US government sensors, do not have that same pattern because they're not as sensitive to high velocity objects. So a lot of biases. Why do we care about them? Well, they affect, again, what population GLM is detecting. It could really be that most GLM detections are meteors that are just faster than 50 kilometers a second, which is not really what was anticipated, I think, a priori. But we can't really confirm this without velocity data because GLM is not very good at reading velocity in the objects it detects. Any population studies that use GLM data will be affected by these biases. And also these biases might help us understand in individual cases why a particular object could be detected by a ground-based system, but not GLM. How do you deal with these detection biases? Well, there's this paper here where I deal with them, and we're able to deal with pretty much everything except for velocity because, once again, we do not observe the object's velocities, and so you can't really adjust for their velocity. Okay, now, so much for detection biases. Now, there are some issues with the radiometry. First of all, at the edges of the GLM field of view, the calibration can be way off because it's designed for lightning, not for bolides. Also, the pixels perform adaptive background subtraction. So if you have an object lighting up a pixel for a long period of time, that light starts counting as background and starts being subtracted from the light at later time steps, which will mess up your light curve a little bit. And there's some other issues as well. And you can see here, the raw light curve looks like this in this particular pixel. But then when we correct it, the shape of the light curve changes quite considerably. So it's important to be careful with the raw light curve data coming from GLM. And there's this paper, correction calibration of atmospheric impact observations in GOES GLM data, which has an extensive treatment of this topic. Okay, so that was a lot of negativity. I'm sorry. We're here to have a good time. So let's see some happier results, perhaps. First of all, through my work with GLM, we're able to fix an issue in an impact model, which changed predictions for how we expect asteroids to impact the Earth across different latitudes, how many we expect at different latitudes. So that was a success of GLM data. Also, the fact that GLM picks up on meteor showers quite strongly, I think is kind of incredible and very cool. And in particular, you can see that for particular meteor showers like the Leonids and Perseids, you can predict how many GLM should see at different latitudes, right? And then the actual observations through various statistics and modeling, because we can't actually attribute different events to meteor showers or not meteor showers. Through statistics, you can actually see that the observations align with what we expect. So this is, again, success of GLM. Through my work, addressing things about GLM, I also developed some models which allow you to basically simulate expected distributions of impacts across the surface of the Earth, where you can filter it in various ways using, various models of asteroid or meteoroid populations, including the Meteoroid Engineering Model 3. And you can make predictions about diurnal variation and the flux across latitudes. Finally, just hats off to Dennis. I lifted this from Nature Astro paper by Dennis. And you can see that GLM was used to sort of fill in a really detailed light curve for this particular object and was key in that analysis. And again, here Dennis was very careful with calibrating the light curve of GLM through some various techniques. Also, there's other interesting research where people have used GLM to look at the upper mass limit for stream meteoroids. Because again, huge collecting area, so you really get to see a large population of large objects. And finally, there's this interesting figure here where I worked a little bit with trying to actually use GLM to compute trajectories of bolides. And you can see this is what the camera sees, right? It's just, if like here 7 pixels lighting up, here 4 pixels lighting up, then each pixel is lighting up hundreds of times, and you can see how different pixels light up at different times and with different energies. And so you can sort of, the GLM sees it on the ground effectively is how it's calculated. But then because of the stereo nature of the observation, we're able to sort of reconstruct statistically what the trajectory was. And this is kind of funny because it ends up looking like, some of the methods used in meteor astronomy. But in meteor astronomy, you're looking down from the ground up, whereas here we're looking up from, different points in the sky down to the ground. And so it's very interesting. And I actually looked a lot at methods from meteor astronomy when I was trying to develop these techniques. So future directions, I think there's a lot of potential of interactions between GLM and meteor cameras because, they kind of complement each other. GLM is, all weather, huge collecting area, very high frequency, but low spatial resolution, difficult velocity bias. The radiometry is kind of hard, and it's just low resolution. Whereas meteor cameras have really excellent trajectories, really good calibration, great resolution, but they cover a smaller surface of the Earth, although that is increasing thanks to you guys. Relatively low frequency, and the detection biases can be kind of complicated because you have different meteor cameras going online, offline. There are weather effects. The field of view is kind of complicated as well. Anyway, so these two systems are kind of complementary, I think. And what we want to do is use ground-based data to continue developing GLM-only estimation methods for orbital and physical characteristics because the ground-based systems provide the ground truth, pun intended, that we need. And then we also use GLM to we can also estimate the probability that GLM will detect any given event. Now the question I want you to ask yourselves is how can GLM data be useful in your own work? Now these are some things that I've written down based on this session and the previous session. Maybe GLM data would help in developing daytime camera capabilities, right? If GLM, because GLM sees things during the daytime, and you can check if your cameras see those same things. You can maybe use GLM lightning flashes, which cover a very large surface of the Earth, to improve timing. And finally, maybe, as Dennis just mentioned like a few minutes ago, you could have automated tip-offs to Global Media Network or other systems for fireballs. Okay, and something to look forward to is so GLM is like these two right here. Recently, there there's the Meteosat third generation lightning imager satellite, which came online, and it operates very similarly to GLM, and it provides coverage here, including over many GMM locations. And there's also the Fangyun 4A satellite, which also has lightning imager, which is also similar, and it has coverage here. So it's not just GLM, it's not just, the Americas. There are other systems coming online which can be used. Okay, now finally, very quick demo about software that we've made to work with GLM and GMN and other data. So first of all, there's this data visualizer at belize.seti.org, where we can, for example, hit GLM data here. You get a map of the detections, it's interactive. We can, see which satellite detected it. We can plot fields of view and whatnot. You get nice maps here. I encourage you to all go on this website right now and crash it. Next, global meteor network data. I'm curious, what did global meteor network see, let's say, yesterday? Okay, so we see some detections there. Let's maybe color by the IAU code, right? Oh, let's plot the orbits, where you can see a nice little map of orbits and some very clear, patterns of meteors in the same shower having similar orbits, which, we like to see that. And I can also look at the radiance, for example, a nice radiant plot that you can look around, and you can see different radiants. You can also maybe color by velocity. There you can see, their velocity with respect to Earth, which has this nice pattern that's fun to look at. Also, Python package. Let's play around with this for a second. So this Python package basically lets you work with bolide data and pull data from different sources into things kind of like a data frame if you worked with that, pandas or geopandas. We can load in the GMN data from, let's say, yesterday again. Okay, just quickly downloaded. Can look at the data. It's just like a table, right? That table should look familiar. We can plot the detections. I've included boundary equals goes to show where the GLM field of view is. So that's kind of fun. We could, for example, filter for detections that are within the goes east field of view, and you get a smaller table of 84 rows instead of 448 rows. You can let's see. Oh, we can also make an interactive plot. Let's see. Let's plot the radiance in a stereographic projection. And color it by the geocentric velocity. And this should also look familiar based on the website a few seconds ago. Might take a second. There. And we have an interactive plot. This package actually is part of what drives the website. But yeah, so you can use this package to make various pretty pictures. Documentation is here. There's a lot more that I didn't tell you. It does so many things. I think I might need to fix some things. I tried installing it and the new install in Pandas broke some things. But yeah, it works. It's cool. And if you've ever tried to scrape data from this website for GLM data, or this website for the US government, CNEOS data from their satellites, you don't have to scrape it yourself anymore because the package will do it for you. Okay, yeah, that's all I have for you. Thank you for inviting me, Dennis.
Amazing work. I mean, that's hopefully you're going to inspire a lot of people to start using these tools and start digging through. Yeah, they're asking you to drop the link in the chat if you don't mind. I'm sure that the website is going to crash now. So there you go. That's awesome. Are there any questions for? Oh, Bill Cook has a question. Bill, go ahead.
Excellent presentation, Anthony. Thanks very much. So I got two questions. Number one, so you're unable to determine speeds. So when it comes to making a shower identification for GLM, my guess is you use a temporal correlation correlated with the visibility of the radiant, since you can't measure speed, correct?
Yes. So in my work, we didn't because of the various technicalities of the model, we didn't use the radiant of the horizon, but we used temporal correlation because the main thing I was looking at was GLM during these shower periods. It detects an excess, right? And then you can model that statistically and basically see like, okay, what is the latitudinal variation of whatever excess you're seeing? And so we've never really made actual shower identifications using only GLM data. It's all kind of like probabilistic, right? Because during a shower, you see some sort of excess.
Right, but so my question centers on that. The Leonid radiant is embedded in the north apex source, and I've been doing this for decades now. And an example, Chandra in 2003 was hit by a meteoroid near the Leonid peak. So the program attributed to the Leonid, but if you check the data, it was more likely it was a north apex meteoroid because the Leonid flux was below the flux of the north apex source at that time. So my question is, if you're doing this statistically, how are you taking into account the fact that shower strength varies from year to year? I mean, it's kind of not a statistical thing. I mean, the Leonids are not constant. So how are you dealing with that?
Yeah. So the goal statistically was not to actually measure the meteor showers themselves. We were interested in the sporadic flux, and so we were sort of just like using these tools to roughly remove the meteor showers. It was nothing exact. The goal was to measure the latitudinal variation of the sporadic flux, and we noticed that things like Leonids and Perseids were messing with that because they're more from the northern sky.
And that was based on the temporal correlation and not
Yes.
much of anything else, correct?
Yes.
All right. So my second question has to do with the fact that GMN does not automatically detect fireballs, yet your website is dedicated to bolides. So what you're seeing with GMN are millimeter-sized particles produced by comets, whereas a typical GLM bolide is produced by asteroidal material. That transition occurs in the several kilogram range. So isn't that kind of a little bit misleading? Because, a casual user looking at your site would think that all the GMN stuff are bolides.
That's a very good point. We hadn't thought about that because we designed it first just for the GLM and the USG data, right? And so we called it like the bolide visualizer, but then we thought we might as well just include other data sources too because we could, and it was kind of fun and cool to do. But then we didn't change the name. That's a very good point. I will see if I can maybe add some clarification text. Thanks.
Awesome.
Thank you very much.
Thank you, Bill, for a great question. There are also a couple of questions in the chat. If you don't mind answering them in the chat, and we're going to move along. I got a pre-recorded talk from James Scott. I believe that he is currently in Antarctica or on the way to Antarctica. So he couldn't make this, couldn't make the meeting, but he sent a recording. So just give me a quick second here for me to set this up.
Hi everyone, thanks very much for the opportunity to give this talk. I'm going to talk about New Zealand's community Meteor camera network, which is known as Fireball's Aotearoa. That's the indigenous name for New Zealand. It's something that we've spent a lot of time trying to engage the media with and also interacting with the public, and that both has its strengths and weaknesses. In February 2022, there were 3 cameras across New Zealand, and they captured a total of 210 meteors. By November 2023, there were 120 cameras active, and there were 4,200 meteors imaged in that month, although it was a time of meteor shower. But still, we've had a more dramatic rollout in the last year and a half of cameras across the country. You can see they're present in the North Island, up here, the South Island, Stewart Island, and also on the Chatham Islands here. Mostly deployed in schools with the public and in observatories across New Zealand. As part of the program, we've set up a mailing list, there's a website, and the project is now part of the Royal Astronomical Society of New Zealand. And the reason for doing that, linking with that society, is that it's to make sure that the camera section stays active for a long period of time. You can see that the network coverage is pretty good. This is coverage at 25 kilometres elevation, and you can see that almost all of New Zealand is covered. Not quite everywhere, but it's pretty densely packed. And this is really good because what it enables the camera network to do is if there's a camera not functioning, or for example, there's weather overcast in some area but not another, then we've got a kind of a critical redundancy built in there that we've got enough cameras to cover in those cases. Here's a pan through the Geminid cameras, or the images captured by the cameras during the Geminid meteor shower last year. And you can see that with our nationwide coverage, we picked up a huge amount of meteors through that time. This is just pasted into Google Earth, which is a very useful way of conveying data. The cameras themselves, we try and stress to the people, the hosts, that they're very simple to build. Often we have a kitty that we build a series of them, and then we can sell them to those people as they become interested. In most cases, they're single stations, but in some places there have been multi-stations built up, and they are connected by Raspberry Pi, separate Raspberry Pis, or they've been turned into a Linux box. This one here is near Queenstown in New Zealand. It was mounted on a high point, and so it's got pretty good coverage of the night sky. The data are predominantly shown on the Global Meteor Network. We all know this. The purpose of showing you this is to show, for example, what some of the nice coverage was in recent times. This is images of the Geminid field from one particular camera. But of course, we had lots of these cameras active, and so there was lots of data collected. But you can see a very strong preferred orientation of the meteors, or a couple of preferred orientations, which actually represents multiple meteor showers. The cameras capture quite nice videos. This is really good for the public. They really like being able to see what their camera hosts. And this one isn't brilliantly placed. It's catching a little bit of light from the street down here, but it's not doing too badly. Great for engagement. And when there's a big fireball in that, of course, you can shorten the video and share that with the media. And one of the features that's really neat about it, has been trying to get people to engage with the radiant maps. So in this case here, this particular camera, NZ002X, collected 76 or recognized 76 meteors, of which almost 60 of them were from the Geminid meteor shower, or the radiant, the Geminid radiant, and 16 were from the Hydrid radiant, and then there's a couple from a couple of other places as well. But during these peak meteor showers, these maps are absolutely stunning. And not only do the cameras capture astronomical phenomenon, but they also capture weather phenomenon. And in this case here, we can see that this camera has got a meteor, which is what's triggered the meteor detector. There's a bunch of satellites around it, but it also captured a series of sprites. So these are the discharges above a thunderstorm. And we've had some really stunning sprite fields for the last couple of years. The cameras have caught comets, and just work through these one by one. But here, this is again a Google Earth image with some of those trajectories plotted on there. In March 2022, there were two comets exploded high above New Zealand. They were quite dramatically seen. Here is one of them here, caught coming in up here and exploding. Actually exploded quite high up. And then with the camera data, we can tell the velocity of those. So that one was traveling at around 70, an average speed of about 70 kilometers per second. So that's pretty quick. And it flashed across the night sky in just over 2.5 seconds before exploding. And the elevations appear to be from about 140 down to 90 kilometers. So this one got nowhere near the ground. Here we can see the orbit of that particular meteor, and you can see that there's Earth in a solar system, and the orbit of that meteor indicates that it came from far out. And it's well off the plane of the ecliptic as well. So it's probably from the Oort cloud at the margins of the solar system. And as a comet, most comets tend to appear to explode quite violently high up because they're inherently weak. And there's the trajectory for that particular event. So the cameras have got comets, and we've also had some fireball occurrences. This was actually in 2022, but it still remains a pretty good example of the network capturing something useful. A bright fireball trajectory coming in here, also in the South Island of New Zealand, with a target area of somewhere in here. The Struan field was actually resolved to a much smaller area than that. The short video there shows this fireball, and this is a really good one because many of our public people don't realise what a big fireball is. They see a small flash across the sky and assume that that's going to be quite a significant one, but really we know that it has to be really bright and saturate the camera lens. And that particular fireball, the velocity was somewhere around 12 kilometers per second as it traversed the upper atmosphere, and then it dramatically slowed down from about 40 kilometers down to less than 20 kilometers, down to a velocity of just a couple of kilometers per second. Relatively slow, extremely slow, in fact, for a meteorite or meteor. And that actually resulted in a search. And you can see the community, or part of the community, we ended up having about 100 people searching in gridded patterns, trying to find signs of the meteorite. Unfortunately, it wasn't there, which is kind of a shame because it's estimated there was about 10 kilograms of material, or at least at that final stage. But the key thing about it was that there was massive public engagement with the search. The media really got on board with us. And most recently, the New Zealand Camera Network had some success imaging a new meteor shower resulting from Comet 46P Wirtanen. That meteor, that's Wirtanen there, that was actually captured by one of our members in 2018. The comet orbits every 5.5 years. And let's go down. It was predicted to the debris that was knocked out of off the comet's surface in a 1974 encounter with Jupiter was predicted to reach Earth on December the 12th, 2023, and only really be visible above the Southwest Pacific down here. So the New Zealand network down here was perfectly placed to image it. It caught not heaps, but some of the larger particles that were visible. There is one of them captured by NZ002X. And then on the radiant map, it's this little area down here. So on that particular evening, there was an increase in meteors, or a meteor shower down here, defined largely by the New Zealand network, but also by the Australian network. But the point of this is that this is based as a citizen science project that now has research outputs. And the media love it. We've had lots of coverage from various places, although this has a bit of a feedback effect that the more coverage we get, the more people wanting cameras we get, which results in more images, which results in more media interactions, which results in more cameras. So there's huge outreach potential as a result of this, although it can get pretty intense. There's really good opportunity for meteor engagement if you can quickly convince the media to get on board with a meteor hunt event or a big meteor shower or a bright fireball. And you can get student engagement, and there's also good promotion of the host location. So in summary, the network's been pretty easy to build, although we've had to continue to support it over the time it's been running. Many people have a camera but need support to manage it. It's been operating by pre-building cameras and then selling them at about 550 New Zealand dollars per camera, which is not very much. We've had excellent public engagement, although, as I said, that has a feedback loop. And we find that many people want to be part of this, despite having no astronomical background. And so there's a lot of potential to interact with communities that would not normally engage with this sort of stuff. And best of all, it's now contributing to scientific goals. The cameras that in my system have been largely built by students and some of the later members of Fireball's Aotearoa.
Okay, that is James's talk. Hope you enjoyed it. One thing I must say is that the New Zealand network is one of the most vibrant ones, and one of my favorite uses for a Meteor camera was actually when people look at their, I believe, a local road, and they're watching their neighbors drive by at 2 a.m. and they're wondering where they went. So our cameras are used for other purposes as well, not just meteors, which I find really fascinating. Okay, so next one up is Lexi Wallace. She's going to tell us about their STEM initiative and their outreach program at Perth Observatory. So Lexi, go ahead.
Awesome. Thanks for your patience, everyone. Hey, I'm Lexi. I'm from Perth Observatory. I'm the STEM outreach officer there. I joining today to share a night sky camera project in Western Australia, which was a STEM initiative to connect regional sites in Western Australia to the global Meteor network. And we've just finished the report for Inspiring WA that helped to fund the purchase of 15 cameras to deliver around Western Australia. So Perth Observatory, just a little bit, we have been around in WA since 1896. It's not that recent compared to a lot of places around the world, but Western Australia was sort of settled in about 1830. But of course, the Indigenous population, we think, have been here for 40,000 to 60,000 years. So it seems like, 100 years feels like a lot of time, at least for WA, but we know that the first astronomers here have been here for a long time. We were really important for timekeeping. The picture on the left is our old site in Kings Park, right in the centre near Perth, the capital city. And light pollution in the 1960s meant that we moved about 30 kilometres east to the hills. And this is a capture of an aurora by one of our staff and volunteers looking towards the south. You can just see the Southern Cross as well to the top left. So we've got lots of telescope domes, and we were involved in research for quite a long time. We lost state funding in 2013. At the time, we were the last observatory in Australia that was still state funded. And the place nearly closed down, and it was just because of volunteers that we were able to keep the place open. So in the bottom right, if we've got any Star Trek fans, I'm down the bottom in the middle with a lot of our volunteers and guests for our special Star Trek night. We predominantly keep the place open by running tours, but we've recently received funding to expand our STEM outreach activities from the state government. So when I started as a STEM outreach officer last year in June, I'd been volunteering for a few years and knew quite a bit about the observatory and helped run tours. I knew that we had these Global Meteor Network cameras on our roof, and you can go to our website and actually view our footage from Perth Observatory. Dave Rowlinson helped to set up these cameras, install them, and also set up these time lapses to go straight to our website. I thought this was awesome. At the time when I started, I hadn't actually met Dave, and I sort of brought Dave into the project by applying for the grant to get the cameras. And then I think after I applied, I actually had a meeting with Dave just on Teams to sort of say what I was hoping to do. And we were successful in receiving about $4,000 to buy 15 cameras for this project. So our original application in the left, which you can see, I applied and actually called it Fireball cameras. At the time, I didn't actually know about the Desert Fireball network. My background is actually in neuroscience and linguistics. So I did science and arts at university and always had a passion in science. And I just wanted to draw back to something Dennis said earlier, that meteors can spark a lifelong addiction to science. I think for me, I saw Comet Hale-Bopp in 1997, and it's only really recently that I've come to appreciate the connection between meteor showers, comets, and asteroids. And so it's quite exciting. But Fireball Cameras was the original title. Once I found out about the Desert Fireball Network, we renamed it Night Sky Cameras, and we put that an expression of interest. So instead of contacting sites to ask them to get involved with the project, we had a questionnaire asking about their outreach potential, their location, whether they were interested in covering the installation costs for the cameras, and we left it open to anywhere around WA. So we received 51 applications, and as you can see, WA is quite a big part of Australia. I think it's about 2.5 million square kilometres. So it's quite a large region. And when we applied for these 15 cameras, originally we just wanted to do 3 sites and have 5 cameras per site. But because we had such an awesome number of applications, we decided to just do 1 camera at 15 sites. So these are the sites that we have chosen. We actually couldn't handle bringing it down to 15, so we chose 16 sites that are listed here. So it's a mix of sort of public centres, museums and attractions, as well as education sites. So some of the sites are primary schools, some are high schools, and we've got 1 TAFE, which is sort of like a tertiary education opportunity, sort of like college and university, but the courses are generally a bit shorter and more entry level. So it's an awesome list of sites that we've got. Some of the things that we've learned through the project as we started to roll out the cameras is that the installation costs can be quite high. So while it's quite easy to install a camera at your own location, when you're installing cameras or delivering them to public sites through a grant project, usually a requirement of the grant is to meet local and federal legislative requirements, as is the case in private. But it means for installation that in Australia, if you want to run an Ethernet cable through a wall and drill a new hole, you actually have to make sure that the person doing that is registered with ACMA, which is the Australian Communications and Media Authority. So generally that can be a cabler or an electrician, but it means that the installation costs can actually be quite high to install the camera. So we found that the cost of the Raspberry Pi and camera installation costs were generally higher than the actual cost of the camera station itself. Adding on top of that, regional WA is generally not that populated, so a lot of the qualified electricians or cablers have to charge for travel to head out there. We also found that the cost for the PoE injectors, power over Ethernet injectors, was higher than we had budgeted for, because we ended up going for one that met Australian standards for electrical equipment. So some of them have a tick that you need to sort of look for. The ones that you order online, they still work and it's okay. But because we wanted to sort of tick the boxes for this big grant project, we opted for ones that, sort of met those standards. And we also learned a lot about network configuration for public sites. So generally port 22 is blocked. And yeah, Dave and I have been working, mostly Dave has been working through that with these sites. So here's a picture of some of the equipment, learning how to build the camera. Dave Rollinson showed myself, Jeff Scott and Patrick Zimmerings, our other Perth Observatory volunteers, how to build the cameras, and we did a lot of the testing. So it was really quite fun. I think it's quite easy. The hardest part is sort of getting rid of the infrared filter. I think it's just the first time you do it. I was lucky the first time, but it can be a bit fiddly. But apart from that, it was awesome to see that it's really something that you could have for workshops, as the outreach project has already been doing. So once all those cameras were ready, here's Dave Rollinson, myself and Patrick Zimmerings with a box full of equipment ready to drive out to some regional sites. And on the right, just before Christmas, there's a little Christmas tree in the middle there and a Meteor camera. And we got to deliver quite a few of these cameras out to regional WA. So most sites are really excited about the community engagement aspect of it. And then they're slowly learning more about the Global Meteor Network. So on the left was a picture that I took from Meteor I can't remember the github.io, I think it's Meteor map, showing the camera stations in WA. So Perth is sort of down the bottom left there. And then the one in the middle is some of the camera stations that we've helped to install. And the one on the right showing Meteor map, I think this is mostly Dave's fault that WA has such a massive catch of meteors at the moment. And it's quite cool as well hearing from the Desert Fireball network, because the GMN cameras are more sensitive and the Desert Fireball network can pick up the really bright fireballs. It's been awesome to see as well that the DFN and GMN can actually work together to help plot meteor trajectories. So Perth had a really bright event in November last year, and you know, we were able to calculate the trajectory, and if there was anything left, it landed in the ocean. But it's just really cool to see the two initiatives working together. On the right, you can also see towards the top, there's a little lone meteor. So that's Carnarvon Space and Technology Museum, and it's the first recorded meteor in the Pilbara region from the GMN, which is quite exciting. So these are the station IDs and the locations again, the delivery dates, the installation dates, and calibration dates. So we've still got a few more to go. I think since I made this table, we have had, I think we've only really got 5 sites left to sort of connect. Karatha has just installed in the top right. That's the northernmost camera station that we delivered to. They've just had a cyclone pass through, so I'm impressed that they actually got that camera going. And so we learned a lot about you know, WA being such a large geographic region, there are different requirements in the different areas, and the temperatures around here as well can get up to 46, 49 degrees Celsius. So something to consider. Here's that trajectory in the Pilbara, and I think this was, I believe this was the fireball that was captured, and it's quite awesome that the Carnarvon Space and Tech Museum was involved in the 60s during some of the first moon landings and relaying some signals to the rest of Australia and the world and NASA. So it's quite an exciting site to get involved with the project. Like Dennis said, WA is a great place to find meteors. And as well, it's a great place to see the night sky. So these regional areas, they're not highly populated. There's lots of stars that you can actually catch. So this was captured in Perenjori, which was just a brilliant place to view the night sky. Awesome fun. Busselton Jetty, which is down the southwest of Western Australia, they have got one of the night sky cameras. We went there to do a talk as well. They have an underwater observatory, so it's quite exciting. They live stream their cameras during the day, and they want to live stream their night sky camera, their Global Meteor Network camera, during the night as well. So Dave's helping them set that up. So it's quite exciting. It's sort of the first underwater observatory as well as night sky observatory, at least that I know of. So I've got an image on the left here showing our event in Kojonup. We had a night sky viewing session. In the middle, there was a picture of me doing a talk, but I've accidentally ruined my slides. But if you just imagine, we've got a PowerPoint set up and around 40 people attended from the local community. It was a free event, free food, and we got to share some cool new pictures from the site. So on the top right, you can see a Starlink train passing through, which was really cool to see. I'd seen Starlink trains before, but when I saw it on the captured footage weblog, I didn't actually recognize what it was. So Dave helped me out with that as well. So we've had a few more public outreach events with this. We had an open day. We went to a planetarium. Dave helped write some code to tile a bunch of the videos onto a massive projection planetarium screen. And we also went to Meteor Lab at the WA Museum to share a bit about the project. I think one of the coolest things has been to share what a meteor shower actually is, and that we can predict them as we know when Earth is actually passing through that sort of debris field, and showing images of that, I think the public had a really good response to. We've had an awesome amount of media attention from this project. So in the past few weeks, we've had the Australian Broadcasting Commission, the ABC, wrote an article once that article was published, I spoke on the radio as well as live national TV about the project, and Dennis was interviewed as well. So I've got some links on the next page if you'd like to have a look at some of these recordings. And yeah, I think it's quite exciting to involve regional communities in a scientific project, as it's quite expensive to drive out and engage them in science. So having this opportunity to host a camera, it's an opportunity to engage them in an ongoing way. So the engagement that we had sort of amounts to more than 200,000 views of these videos and pages, which is awesome. And you can have a look at these links if you'd like to read the articles or have a look at some of these videos. We've already gone through that one. So next step for us is working with Redim to see if we can develop the GMN outreach project for schools in particular. So there's a lot of schools that are really keen to get some of these projects going. One of the things that I would like to do is connect it to the school curriculum, because teachers don't have a lot of time to work out whether or not something fits, ticks the boxes that they need. So I think the Desert Fireball Network, I've been talking to Ellie and Hadrian, spoke with them last year, and we're hoping to work with them as well as other organizations to use some of the content they've developed in the past, so more than 10 years ago, and try and connect it to the Global Meteor Network Outreach Project. So Redim and I are looking to sort of coordinate that for Western Australia, but it's still in the really early days, so it's something that we're going to work on. Cogenut, one of the sites, is really keen to use, for example, the Constellation sort of project to connect to Indigenous astronomy. So there's a lot of different Aboriginal really important stories about the sky and observations that were made, and trying to bring the project to be able to share some of the knowledge that's been held for thousands of years would be quite exciting as well. So this week I was able to talk at Questacon STEM Futures workshop to about 20 or 30 teachers and leaders in WA about the project over the last couple of days. Also talking at the Science Teachers Association of Western Australia Constawa conference on Tuesday, April 8. The theme is species survival, so I think this ticks the boxes for that. And then Redim and I are sort of looking at having an outreach meeting probably for Western Australia, but really if something's online, it's open up to a lot of different sites. I haven't put it on the slide, but I'd also like to definitely connect with the other outreach sites, like in South Africa, Germany and the UK, because I've read a few of the projects online, but I'd really love to be able to talk to some of the leaders there. So I thought that maybe I'd just end with one of the, oh, not this one, it's on the next slide. That's from Cogenut. So Dave helped to make this tile of some of the cameras that we've set up. So if the video would like to work, that's okay. It's not working. Oh no, here we go. So just being able to see how many stars you can see from regional WA and the number of events that's going on. I think it sort of blew a lot of people's minds that, like, the teachers that I spoke to this week are amazed that there's that many meteors and satellites up there in the night sky. So yeah, that's about it. If there's any questions, let me know, or you can reach out to me by email.
Awesome. Thank you for a wonderful talk. And I think Western Australia is very lucky to have such driven and talented people and volunteers such as you, Dave, and others who are involved in the project. Are there any quick questions for Lexi before we move on? Well, you can always put your, oh, Derek has a question. Derek, go ahead.
You're mute, Derek.
Oh.
Okay, sorry. Yeah, it'd be really good to link with the outreach programs over in Victoria. ASV have quite a major outreach program. We've got some interest from Canaiva and I'm trying to get ASV to develop, to look at what you've been doing over in Western Australia and doing something similar over here. So
Yeah.
great, Lexi.
I'm actually coming over to Victoria in July and start of August, so potentially I'd be able to meet in person as well to have a chat. So
That'd be fantastic. Yeah, we can make the right connections over here. So yeah,
that would
yeah,
be
great.
awesome.
Okay, we'll be in touch.
Thank you, Derek. We have Peter McKellar. Peter, go ahead. Oh, Peter, we can't hear you for some reason. You are unmuted, but the audio is just not coming through. No, still nothing. No. Okay, let's go to Ken and Peter. Would you mind trying to fixing, or maybe just put the question in chat if you don't mind? Thank you. Ken, go ahead.
I'd just love to say a big thanks to Lexi and the team and David for making this project happen. It's absolutely awesome, and it's great to expand the network in WA. Top job.
Thanks.
Yeah, I feel like I actually missed really highlighting Ken. So Ken runs Astro Star Tours WA, and after we gave a camera to Ken, how many cameras have you built since then, Ken?
I've got 3 more added as well, so I've got 4 now. Obviously, it's daytime now, so I can't see the cameras, but yeah, I love that I can click a button and see my cameras. It's awesome.
And just to share as well, so Ken's one of the sites that doesn't have an actual public location, but because Ken runs a lot of outreach online as well as in person, we felt like it was a really good opportunity. And I think that, being able to find those people that are really going to be enthused by the network is the way to go. So it's been awesome to connect.
Peter McKellar, would you try again, or no, all good. Okay, I think we're good to move on. Thank you, Lexi, again for the wonderful talk. And next one up is Peter Eschman.
Okay, let's see if I can get my screen share going. Hopefully you can see that all right.
Yes, we can. You're good to go.
Okay. I've served as local area coordinator since we started our adventure in 2018. Our New Mexico Meteor Array is a collection of cameras as a group effort, with members contributing wherever they can. I want to thank a few people who certainly contributed more than their share. Steve Kaufman runs a Pi 4 with SSD drive as our local server and is upgrading it soon to a Pi 5. Steve helped develop our external script and other support files. He keeps us on track by sponsoring group meetings on Zoom every 2 weeks. Gene Mraz helps us optimize camera locations, azimuths, and altitude settings. Steve Welsh helps me build and configure cameras. And Bob Huffnagel uses his mill to trim metal camera case visors. This removes the obstructions from the upper corners of images taken with our 4mm lenses. He has also attached many end connectors on camera pigtails. There we go. We have 28 GMN stations in our camera array located in southwestern US. Coverage is centered on the intersection of 2 interstate highways in the Albuquerque metro area, extending 420 kilometers north-south by 225 kilometers east-west. This map shows most of our stations. It's missing several we've added in the last year, and also missing several yellow markers for new Lowell Observatory Project 6 camera stations in eastern Arizona. This shows meteors detected in January of this year. The New Mexico meteor cloud is on the right, Arizona's in the center, and California's on the left. The New Mexico state boundary is shown in orange, and the US-Mexico border is shown in green. For scale, the right or eastern boundary of New Mexico is 556 kilometers or 345 miles north-south. Every year we see larger event clouds with smaller gaps between them. And we do hope to get a little bit better coverage in this area if we can make that happen this year. We have 11 cities and 16 operators with 8 cameras in Albuquerque, 2 in Edgewood, 5 Santa Fe, 6 Las Lunas, Belen, 2 Socorro, 2 Magdalena, and 1 each in Quemado, Taos, and Creede, Colorado. We began in February of 2018 when I bought an eBay IMX 225 station built by Dennis Vita and Mike Missouri. In the fall of that year, we ordered 14 stations from Dennis and Mike, which really got our Meteor array going. In the spring of 2019, Dennis was kind enough to help me order parts to build 14 more stations, and we sent 3 to California. We bought more parts and built more stations and continued to grow since then. We use 4mm lenses on our IMX 291 sensors. Our Pi stations use at least 128 gig micro SD cards, allowing for 5 nights of captured data. They have 256 gig USB thumb drives used for automated data backup each morning. We only have 1 station still running Pi 3 Jesse. 14 cameras are on 4 gig Pi 4 running Buster or Bullseye. 2 are on 1 Odroid system, and 14 have moved to multicam Linux systems running Ubuntu. Pi 4 are much better than Pi 3, and Linux systems offer even better results by running multiple cameras on a single system. The Linux systems are rock solid, and it's very convenient to be able to work with multiple cameras from a single remote connection. We hope to extend our coverage with several new 6-camera multicam Linux systems later this year. My testing has shown that Pi 5 can run up to 4 cameras, offering new options for GMM. I discussed Pi 5 in the earlier conference session earlier today. Times have changed. Early on, I learned it was impossible to monitor this many stations by logging into them every morning. We invested considerable effort automating station data uploads to a local server every morning. I used to run cron jobs starting on a Pi 4 and later a multicam Linux that copied data from our local server and transferred it to display on a local website. This system was developed because our stations were not on InstaStream at the time. Now I use a cron job on multicam Linux to download the US HTML from the weblog. I run a Python program to create a smaller HTML file containing only our stations. The program also creates a subset sorted by camera azimuth, and then both HTML files are uploaded to a local site. The local site displays results sorted both by station ID and by camera pointing, because we found it's easier to spot shared meteors when you view images organized by camera azimuth. Our HTML displays the number of stack bits files in the title above each detected stack image. This number is extracted from the end of the stack file name. This extra information helps me quickly check the status for all of our stations every day. Our local site is automatically refreshed 3 times a day and serves as a resource for public outreach. Each morning, I rename the previous day's HTML to yesterday's date so I can review results for any given day. This processing does not take a lot of resources, and a Pi 4 can do it easily. As our experience has grown over the last few years, we've developed an external script that automates 4 tasks. First, it writes diagnostics to a station text file, 1 line per day. This includes number of captured FITS files, any shortfall from the expected total, the number of FITS files in the detected stack, a warning if photometry is missing, and a warning if there's space for only 1 capture directory. The second task is to upload data to our local server, and to a station owner's site if they so desire. The third task is to delete old data. We started doing this well before the new config storage variables were introduced. Our system can also limit the number of capture directories, which is useful on multicam Linux running large storage streams. The fourth task is to back up the night's data to USB drive. However, some people feel they don't need local storage because it is handled by GMN servers. Over time, we've developed a few utility scripts to help with things like automatically backing up to USB drive, deleting data, toggling camera settings, and cron jobs that make sure data is copied to our local server. The first two utility scripts run by our external script each morning on our stations. I have some thoughts about an area coordinator's roles and duties. Do your best to keep things on track. Automate tasks wherever possible to reduce your workload. It's best to monitor all your stations from a single site. So use the GMN weblog and organize your stations using the new config file variables, weblog description, network name, and camera group name. This makes it much easier to find your stations with a web browser search. For each station, confirm that the date for latest night matches the date for latest successful calibration. If dates don't match, did a calibration fail because of clouds during the night? Or perhaps something's gone wrong. Maybe a camera's moved, there's a cable or hardware problem, or the plate par needs fixing. Automate housekeeping so there's room for several capture directories, giving you time to locate fireball data within a few days. Automate periodic disaster recovery backups to USB drive or to website. Here are a few more recommendations. Use remote connections to distribute utility scripts and standardized stations, help with hardware and software problems and upgrades, and fix failing stations. Relay information from the GMN forum to your local group. Coordinate with other GMN groups in nearby areas. Distribute tasks among station owners to help spread knowledge and skills, and promote public outreach. For us, the payoff for coordinated efforts are 3 events that have resulted in stream fields. One in Albuquerque metro area, one to the west, and one south of Albuquerque. As a result, we're now organizing and recruiting people to help with ground searches. This is a new and challenging effort. I would suggest that you begin planning your strategy for ground searches so that you're better prepared when something hits the ground near you. I'm going to suggest a few resources for people just starting out. As I said earlier, use a browser search to check your weblog results every day. Read and reread the GMN wiki. Our wiki's being improved all the time, and we all need to remember to check for updates. Consult Mark McIntyre's excellent wiki, and subscribe to Global Meteor Network at groups.io. I've run out of time here, but I'm going to go out on a limb and request several RMS improvements that would reduce our local error checking and would be very beneficial for others. I'm happy to help with these, but I'm not very good at coding in Python. First, we found that the total number of FITS files captured each night is an excellent indicator of how well things have worked. It would be very nice to have the number of stacked FITS files appended to the file name for the captured stack. When the total is part of the file name, it's easier to extract for station stats. Second, the number of detections distilled by machine learning is buried in the log file. It would be nice to have that number appended to the file name of the detected stack instead of using the number of FITS files in that stack. These ML filtered numbers are a much more accurate measure of Meteor activity. Third, it would be great if the weblog titles for both stack images could include these new numbers from the end of each stack file name. Fourth, please show a predicted number of FITS files following the terminal message that lists capture duration. And fifth, it would be great if the log file contained a summary message that included the number of detections after ML filtering, any shortfall between the number of captured versus expected FITS files, and how many minutes of capture were missed from any shortfall. Thank you for your time today. I'll be happy to address any questions or comments you may have.
Well, thank you, Pete. The last action list is something that we can add to our list on GitHub and list of issues, or put it somewhere on the forum to discuss. And I'm sure that's something we can we can address over the long run. We just have to agree on the best way to do it. I personally advocate for one file that contains all the status messages and something that is both human and machine readable, to keep the consistency of file naming. But I think that's a discussion that should be done off the meeting. Good. In the interest of time, I suggest that we maybe discuss all these things during the workshop after. But now I'd like to go to our final talk of the day by Peter Jenskens about his new book called The Atlas of Earth's Meteor Showers. So Peter, go ahead. Peter, I think you're muted, so I'm going to ask you to unmute if you don't mind.
Unmute.
There we go. You're good. Go ahead.
Video as well.
The video. Good. Yeah, go ahead.
So thank you for allowing me to talk about this new book that came out last October, October 24th, published by Elsevier. It's called Atlas of Earth's Meteor Showers, and it's basically a birder's guide to the meteor showers that we've been detecting in CAMS, but also in GMN. So I wanted to point out that the book contains GMN data as published up to the end of 2021. So if you were active before that time, then your data are actually part of the maps that are being produced and add to the numbers that are being produced. In addition, some of the GMN cameras, RMS cameras, were set up in CAMS networks, in and around CAMS networks. Dennis designed the RMS and GMN software to be CAMS compatible, and so it is possible to also upload your data to CAMS. And what that does is it gives you sort of an additional, you know, an additional use of your data. Your data being analyzed and reduced a little bit different than GMN does it. Namely in the scheme of CAMS, and that actually helps with getting magnitudes and consistent beginning heights and consistent decelerations, and all that information is in this book. It's really what made the book. So if you contributed to CAMS over the years, then that data also contributed in this book. So the book is dedicated to Pete Gorel and everybody that helped keep the CAMS cameras in operation over the years. Pete wrote the CAMS software and really developed this system of doing triangulations on a big scale. Pete also helped with getting GMN going, so he deserves this. We publish our daily results on two websites. One is for public consumption. So this is meteorshowers.org. It's a little similar to what you saw earlier, where the radians are plotted on top of a map of the star constellation. So you can see where your radians are located. You can also use this to see if there's new showers and there's some activity. So this is the distribution of maps, the networks that have a lot of GMN cameras associated with them. It started in the Benelux. Paul Roggemans did a big effort there to develop the RMS cameras so that they would indeed work within a CAMS network. And now they are a big part of the Benelux camera network. Then it was adopted by Nick Moskowitz in LOCAMS for a big expansion there, and still running. And then later, Dave Rollison made it possible to include his network data in Australia. And very recently, James Scott made the effort to also upload the GMN data from New Zealand. So if you have networks elsewhere that could contribute, please do. The data from CAMS collected up till July 2nd, 2023, that's what's in the book, 2.7 million orbits. And give you an idea where we are, in 2023, we captured 490,000 orbits, 345,000 of which were done with the old WATEC and XView cameras. So those are the ones running the CAMS software. 145,000 were obtained with RMS cameras and networks that run mostly RMS cameras. That number is going to go up. GMN is expanding at such a massive scale that, really the growth of the CAMS network has come from the growth of GMN in recent years. And it's really good to see. Again, the more meteors with these maps, the better. CAMS has at the moment still some nice coverage in Southern Africa and in Americas. I think that hopefully will also, improve in the future. So Dennis wrote a short introduction to GMN for the book. So this is in chapter 3 of the book, and gives you an idea what the capabilities are, and you'll find that a lot of the position and radian and speed and so on are very similar to CAMS. So it's possible to combine the data. So how to use the book? Chapter 4 has these maps in right ascension declination, which are sort of your common coordinates for radians. Identifies the meteors in 10-day periods throughout the year. So if you find a meteor, then you look on the map, you identify the number. Then that number you can also verify in heliocentric coordinates. There's also a map that shows the distribution there. It looks a little bit different. That number you can then find in the index. The index then gives you a page number. And if you go to that page number, then you'll find a description of that particular shower. And so it has a lot of information in it. The orbit, the dispersions in orbits, the position of the orbit, the magnitude size distribution index, light curve information, you name it. It also has a brief history that sort of summarizes when specific data of this meteor shower became known. When particular data was first detected, and also who did the first models of the shower, and what do we know about the age of the shower and whatnot. It's fully referenced, so it's also like a library. You can go back to the literature and find more information about it. So this is these tables go with a graph. So you see these maps. This is the map of the Tower Hercules. In 2022, there was a nice outburst, and so that added a lot more points to the map. With all the data presented in this sort of maps, that gives you a sense of where what is on the sky. And so that's how you can use the book. You can basically, if you see on the CAMS website, this is our operational website where I look at daily to see how things are going. If you see something strange, like we did a few weeks ago, you see there is a new blob there that doesn't belong. At least I wasn't there the year prior, the year before that. Then you go on the Southern Apex chapter. You look for that period of time in the year. I believe this was around January the 23rd, 24th. You look in that on those maps, and then you can see if there's a shower identified already in the data. In this case, it was shower 919. So this is the Iota Centaurus that suddenly had unexpectedly much enhanced activity. And so this was also nicely detected by GMN. And so because we detected it from Chile with the GAMS networks and GMN from Australia and New Zealand and so on, we have a nice independent confirmation that, yeah, there was a very unusual event here. So these are all the showers that are listed in the book. There's 513 in total. Most of them are long period showers in the apex source. A number are helium type showers. There was both radar showers presented. There's a lot of radar data in the book as well. And so these are the showers. If you look at it with the Tisserand parameter, it gives you sort of a sense on what dynamical type your meteor belongs. This is the Tisserand parameter with respect to Jupiter. You can see there is a cloud of points at high C major axis. Those are the long period comets. Then above that is a group that sort of stands separately, which I call the Medish type showers. You would think these are Halley type comets, but the Halley type comets actually fall in the long period comet group. So Medish is the sort of the lowest numbered comet that sits in that higher group. And then there are the Jupiter family comets, and you can see the Medish type go smoothly into Jupiter family comets that belong to the Mackles complex, for example, and that evolves to shorter and shorter orbits. We have nice light curves. You can see this particular light curve from the Southern Delta Query. It goes all the way down 3 orders of magnitude in terms of numbers. That's the strength of the video cameras, that you can detect very weak rates and very strong rates. If you look at the beginning heights, now we have to limit ourselves to cams because the GMN beginning heights are a bit different than we use in the cameras. Then you get graphs like this. And it basically defines 2 bands. Each band you can give a number, and I divided it up in 3 groups, and you can basically assign a particular shower where it falls along that along these bands. And it turns out that if you take one shower, you see that 2 of these groups show up, sometimes 3, but more components. But in this case, you have a one high band and a low band, so high beginning heights, low beginning heights. This seems to be a property of cometary dust. So cometary dust has both fluffy material and dense material, and there's 2 different types. And you see that in the scattering properties of comet dust. You see that in the studies of dust that come from 67P, the Rosetta mission that visited the comet. It's a very interesting property, and so the ratio of the 2, how many you have in each group, is a diagnostic. It tells you something about the comet properties. We have a lot of information about dispersions, because dispersions in principle correlate with age. Turns out that it also correlates with the magnitude size distribution index. So you can use this book as a sort of a data dump. So you can look for these correlations with age. You can see that when showers age, they become more rich in small particles. We also have deceleration information, and from that we were able to deduce densities of the meteoroids. So how the particles are slowing down when they're coming in. And that shows that Jupiter family comets seem to have higher densities typically than the long period comets do. But there are exceptions, like comet Giacobini-Zinner has lower densities. These densities were scaled on the recent work that was done in Canada with Camo fitting of light curves and fragmentation properties and so on. And so and the densities themselves agree well, correspond well with what's found from that work. So we also have a nice spectrograph built back in 2013. We've been running that since. It's on the roof of Jim Albers and Diana Gilbert in Sunnyvale. They've gathered data for many years, and from that data we reduced 1,005 spectra, derived the sodium, magnesium, iron, and oxygen line intensities. And if you plot those line ratios up, then you see there is something like a normal band, which would be meteoroids with chondritic abundances. And then there are meteoroids that have less sodium, that are sodium poor and sodium free. And it turns out that most of these sodium poor and sodium free particles are associated with this lower band, with higher density materials. And so in some cases, it's an intrinsic property of the stream. In some cases where the streams come close to the sun, it's actually induced by heating, by the objects coming close to the sun. So that information is all in the book. These are all the people that helped collect all this data over the years, all the people supporting the CAMS networks. So my thanks to Dennis for contributing to the book. My thanks for all the network operators for keeping the network running, and to Pete and Dave and Steve for developing the software and keeping all the networks in operations. Thank you very much.
Thank you, Peter, for your talk. Are there any questions? Just as a reminder, after this, the plan is to take a group photo, just as we've done in the first session. And after that, we're going to have a bit of a discussion about a few items. First of all, any questions for Peter?
I have a question for you, Dennis.
Yeah, go ahead, Bill.
So it concerns densities, right?
For sure.
So we have, spent years determining densities with instruments that have the resolution of GMN or CAMS or poorer. And my impression of the data is that it looks like those densities were biased. They were too many high density meteoroids because we have camo densities now, which has 10 times better resolution. So do you want to comment on that? Because I see a lot of density plots that pretty much are going to undergo substantial revision with what we're learning from camo.
Yeah, the more I look at data and just the high quality of fits and playing with the actual models and understanding how densities are actually, how we actually get them, I understand that just the high precision that Camo has is absolutely instrumental in getting the right densities. There's just so much freedom in the models that and if you don't have the right constraints in terms of deceleration and the complexity of the meteor phenomenon that cameras, non-tracking cameras with, it's kind of weird to call them low resolution, but that's what they are, the wide field cameras that don't see what's going on in the meteor, just like the camo tracking camera does. You can kind of fit whatever you want. There are some constraints, but I feel that if you don't directly observe the grain distribution that's released, if you don't have an extremely good idea of the morphology change of the meteoroid when it happens, because we have this idea of just kind of a uniform body. And what we're starting to see now, and there's going to be an incoming paper about the SDAs, is like there are two components, and we had an Orionid paper. It's kind of like has a hard interior and a soft shell, and the soft shell goes away and leaves like what we call a leading fragment. And those things you just simply cannot see with non-tracking cameras. So I feel that Camel can inform the general idea of what a meteoroid is, of the kind of the model, and maybe after we establish some patterns, we can use other cameras to put more constraints or guess validated on a larger data set. But doing anything directly on these on kind of wide field camera data, I would be very, very reluctant to trust that after what I've seen, what I've done with Camel.
So the claim is not that an individual, that CAMS data can fit an individual deceleration profile reliably. The claim is if you observe a meteor shower and you have 100 meteors observed, and you look at the average deceleration, then the numbers you get for density from that correlate very nicely with what you get from Camo. and so that's why we now have a very nice data set. And the quality of that number, of course, goes down when you have less numbers in a shower. The more, the better. And that's in principle also something you can, in the end, do with GMN. You would have to select your meteor so you stick with the higher elevation one. So CAMS, one of the peculiarity of CAMS is that it only looks above 30 degrees elevation. So your beginning height, your sensitivity is in absolute magnitude is constant. But if you do that sort of approach, then GMN data should also be possible to get this sort of information from the GMN in the end.
After a few calibration points, we do have a student working on an interesting approach, and hopefully that paper, when it comes out, is going to spark a very interesting discussion about densities. Yeah, awesome. Okay. Any other questions before we proceed with the group photo? I am going to switch to gallery view. Okay, well, if we don't have any more questions, I am going to ask every one of you to please turn on your cameras. And this time I'm just going to take one snapshot. I'm going to give everyone, again, about 10 seconds. So I'm going to do a little slow countdown. 10, 9, 8, 7, 5, 4, 3, 2. Okay. And save. There we go. Awesome. Thank you. And I would like to give everyone a 5-minute break before we have a final discussion, because I think we've been going for a while without no breaks. Feel free to chat, but see everyone in, what is that, 03:05 UTC. So in about 4 to 5 minutes. So.
Anthony, are you surviving all the rains in California?
Yeah, I mean, it hasn't been so bad. I actually went camping, what was it, last weekend? Because we went to Fremont Peak, which I think has actually a camp system. Yeah, it hasn't been so bad here. I don't know. How about you? Are you in California?
Oh no, I'm in the deepest South in Alabama. You can't tell by the accent?
Well, people move. I don't know. Peter, are you in California now?
I am, yeah. I'm
Nice.
it's still I'm in Mountain View, so if you're in Berkeley, then yeah.
Yeah.
So who's doing the network in Southern California? GMN network. I wasn't aware that already so many cameras were set up there. Not part of the group.
Pete might know. Pete Ashman might know that.
We just got back.
Were you the one that set up the network in Southern California?
No, we sent some cameras to Bob Massey in Southern California, 3 cameras then. And
Okay.
we work with Bob. He's one of our major contact people. And Bob has since recruited a couple of other people to help. So it's a fairly small group right now. I know that Rob Steele is also in California, north of Bob Massey. So they are growing slowly.
Okay. Yeah, if you're looking for sites there, then I do have some people that offered to set up cameras there in the past. And
Okay,
that might
well,
want to volunteer.
I know that Bob has plans. He's with the Riverside Astronomy Group,
Okay.
and their remote site, as you probably know, is GMARS. And Bob wants to bring up a 6-camera single station there at GMARS. Currently, his cameras are at his house closer to the ocean. But yeah, give me a holler and I'll be happy to put you in touch with him. And he would welcome more camera locations, I'm sure.
Cool.
Yeah, he helped with a multicam Linux project that we sort of introduced and more or less finalized last year. And we're also trying to tackle the problem of 3D printing, 6-camera enclosures and things like that, or probably more likely using 6 individual enclosures, but nesting them in one location, which I think is similar to what Mike Mazur is doing now. And yeah, that's definitely a direction we want to go. Ideally, we're going to put one of those 6-camera stations in Corona, New Mexico, and then there's a New Mexico Skies in Mayhill, where there are a lot of private observatories. We'd like to get one there. They're willing to host it. We'll have to fund it out of our own pockets, but what the heck, if we get them to host it, the separation would be wonderful. It would really fill in that part of the southeastern.
That's the southeastern part of New Mexico.
Yeah.
Yeah.
Peter, and then I should probably work with Bob, who's in northern part of Texas there. I don't know whereabouts, whether he's near Amarillo or exactly where he is, but Texas needs a lot more Meteor cameras for sure.
Yeah, I
Peter
agree.
Eschman, are you dealing with Lynn Rice at New Mexico Skies or Grady?
Both of them. Grady's the one that I've been talking with most recently.
Okay, they're good people. We used to have a telescope hosted there.
Yes.
And you know, I can't say you know, I can't give them better compliments. They're outstanding in terms of support. You would not regret placing a camera there.
Yes, definitely. And I had a chance. There was a Dark Sky New Mexico chapter forming for we used to call it IDA. It's Dark Sky International now. And I had a chance to talk to Grady in person at the time. So I'm confident that they'll do a great job of hosting it. It's just a problem of getting it built. I have all the sensors and the lenses, and I'm sure we can scrounge up a Linux box to run all 6 cameras. The sticking point for me is the enclosure. And the Lowell Observatory Project enclosures are wonderful, but they require a pretty good, almost industrial grade printer in order to print such a large structure out of ASA plastic. And the other drawback is if you have to fix one camera, you kind of have to tear the whole thing apart to do it. So we've been thinking more like using the single enclosure that Mike Mazur is using these days, and coming up with a system where we could host 5 around the perimeter and 1 pointing straight up and get the 6-camera coverage that way. That would be with IMX 291 and the 4mm lenses. But like I say, I've got the parts. I just don't have anything to put the parts in just yet.
That's awesome. That's a great discussion. I wonder if we should proceed. We do have specific action items, and after that, the discussion can go in any direction. So Dave Rollinson, he provided a couple of specific action items that we should probably discuss. But before that, do you want to show the data from that NOVA that we detected? So just for context, Dave is writing in that is it fully done or it's on the way? A little module for Event Monitor where you can give it a right ascension, give it a time, and then the camera is just gonna save everything. And in this particular case, it was a very bright nova somewhere in the southern hemisphere, southern skies. There was magnitude 6 or so, and we do have it on the camera. So I think the camera automatically just downloaded everything. So Dave, do you have those images handy?
I don't. I've had to boot into Windows so I can use Zoom, so I haven't got it to hand. Sorry.
No worries. Maybe see it's in Nowhere in Scorpius, and I believe I might be able to.
So just to answer the questions while Dennis is finding the pictures, Event Monitor, there is some code where you can specify a RARDEC and a time, and it will go out to the whole network and say, has anyone got the picture of this RARDEC at this point in time? The code's written. It's not integrated into the published version of Event Monitor at the moment because before anything gets pushed out, we do quite a lot of testing on it because it's terrifying thinking if I take down 1,000 stations, I'm going to be so unpopular. And Dennis has done what I couldn't do, which is not uncommon. And there you have it. Go on, Dennis.
That's basically it. You can see it right here. I've pushed so this is in SkyFit, and I pushed the stars in the catalog down to 7.2 or something like that, and there's nothing marked there, and that's the little nova that got detected. And on the Harvard website, there's a list of people reporting measurements where they actually take a telescope or a DSLR, go and target the object and measure it. With Geomed, we could completely automate it and get a full light curve of the object, no problem. Exactly determine when it became visible and when it what the light curve is over a long period of time. And the resource is there, the data is there. We just need to find a way to integrate us into the pipeline of the chain. But I do fully understand that this is kind of not even a secondary goal, but more of a tertiary goal. It's more of just kind of a demonstration of what we have in the data set, and it's just such a rich data set that we can do so many things. And if someone is interested, the ability is there. Okay, so I think Dave, you also asked. Let me see here.
How bright was this nova?
About magnitude 6. There's I do have a link. Let me just.
So that was from a 6mm lens in down at Pemberton, which was astonishingly just underneath the radiant of the Vertinids one. It was incredibly fortunate to have such a well-built station in that location in that year. I mean, the luck involved in that happening was just unreal.
It was at the right place at the right time, most definitely. So Dave, you did have a few other items, and we did talk about this initially at the first session, but it is a question about data volume, and as you might imagine, that is something that we are a bit struggling with because we have 1,000 cameras sending an average, let's say, 100 megabytes a day to the server, and we do have a ginormous file server where we're trying to make this available. However, we've decided that starting maybe in a few months, we will be moving some of the data to long-term storage and maybe keep only last year of data on the server where everyone can access it, and it's all backed up there. But data older than that is going to be moved on tapes, and what we're going to do is it's still going to be available upon reasonable request, but it's going to take at least, let's say, 24 hours to go and grab it and to restore some of the data that's necessary. It's just a reality we have to contend with. We did think about hosting it somewhere else, but then there's also a problem of data privacy. Because it does contain accurate geo coordinates, and that is something we do not want to make private. I think we made that clear early on, that we respect our operators' privacy, and that would be even illegal in some countries, especially in the European Union. There are issues with GDPR, and we made sure that no private information is connected to any of the data products. That's why there's a code that's anonymous, and if the station operator decides to make that public, in a sense, that's their choice, right? Okay. So Dave also had a question about what happens to the archive files once they land on the server. So all GMN code is completely open source, except for that one little script that runs on the server, because I don't think it's really useful to anyone. And that script really just waits for the archives to land on the server, tries to extract them, and if they change the size within a second, it means that they're still being uploaded, so it doesn't touch them, waits until the next run, runs every 6 hours, extracts them, and then just puts some operational data files into a folder structure, which is just kind of a station at the night, and the config file is there, plate bar is there, the FTP detect info is there, and then you have the trajectory script, which goes through these files and computes the trajectories. That's all in WMPL. That's all public. And then there's a Flux script that is in RMS. That's also public. It just looks at the exact same files. And it's kind of simple as that. It does have a little addition of making the weblog now. It's just a simple Python script where I kind of put a lot of HTML in. It's nothing smart, doesn't use any libraries, and builds the web page literally from scratch, the static web page. I decided to do it that way because I just don't want to contend with any libraries and versions and breaking. And for what we need it, it's good enough. Okay, and then another question that Dave had is, how do other regional coordinators generate trajectory specifications for Event Monitor? And that is a very good question, because right now, if you want to extract any Fireball data, you have to, if you want to use an Event Monitor to get the files, you have to have a good idea of where the Fireball is. And it's kind of a chicken and egg problem, because you're trying to get data to understand what the Fireball is. It can be a bit hard. So the way I usually do it is I look at the picture of the Fireball from the station on the weblog, and then go on Meteor map, and then I look at the FOV, the map of the FOV. And if I have it from two stations, I kind of get a rough idea of where the Fireball is. And I kind of pick those 2 points, and then that's what the Event Monitor is going to extract. Now, that's not really a perfect way of doing it. And Dave is working on some sort of an automated Fireball detector. And the idea is there that we have a script on the Pi that automatically looks at Fireball detections. And in kind of in real time, it produces hits of, oh, this could be a potential Fireball. And then the idea is that once it has something like that, it contacts the server and logs into the server, and the server would have a script waiting to see if there are multiple stations in the area around the same time that have detected something similar, and then that cues Event Monitor and then pulls the data automatically. Now, that works well, I would say, in a kind of a clean, good theory, but I'm afraid maybe sometimes when data is noisy, it might trigger too much.
It
But I
does.
don't know what Dave, what your thoughts about that are.
But yeah, it does. It's lightning, aircraft, all kinds of crazy things set it off badly. How I am tackling that is I have built sort of a dictionary of all the detections that GMM has made and how different cameras tend to work together. And if there's an event that causes a fireball detection in multiple cameras that aren't normally associated with real trajectories, it's probably not a real trajectory.
Oh.
If
Oh.
if so, I'm kind of using the trajectory database we've already got to decide if we've got trajectories. That falls down because people, especially me, move cameras around quite a bit. But we're not trying to, don't let perfect be the enemy of the good. So for every camera that detects a potential fireball event that matches to a trajectory, an existing trajectory, that's a plus point. For every camera that detects a fireball event that isn't in a pre-existing trajectory, that's a minus point. In Western Australia, that works very well because our network was, up until the great work Lexi started, was kind of designed rather than grew organically. I suspect in the UK, where there's so many cameras, it might run into problems. But all I can do is try and get it working in Western Australia and see how well it works in other places.
Yeah, I think the first step towards any automated fireball handling would be really to fix the fireball detector or make it work a bit better, or provide some estimates, some measurements on the fireballs themselves. I'm very much, I'm always warning that that's an issue, but the truth is that the fireball detector as it stands right now hasn't really been touched since 2015, I think. It's one of the first pieces of code that Dario and I wrote in the summer of 2015, during, I think it was just all done in June 2015. It was a crazy month. I think we slept slept that whole month. That's when the whole thing was born and created. But it hasn't really been touched since then and optimized for many of the things and changes. And the truth is that, when you're a student, you have all the time in the world, but now things are different. And finding someone who's kind of talented in computer vision to tackle that problem can be a bit tricky, and who has the time and know-how, right? But yeah. Oh, Pete Ashman has an item. Pete, go ahead.
Well, I don't know if there's any merit in this, but it seems to me what I do is I scan the captured stacks for our stations every day. And it doesn't take very long at all to scan. If there's a bright bolide in a capture stack, it's going to pop out. So can't we have our magic machine learning scan captured stacks for for the what we see in the web log, and try to detect bolides that way? I mean, it's a wish, it's a pipe dream, but seems to me that that's one avenue. Gosh, if we could just hire somebody to scan all the captured stacks.
Well, there is a better way, and that's something that Dahmer produced a graph recently when there was the 2023 CX1 in France, where we had a lot of cameras in the UK which didn't observe the fireball directly, and there were a lot of cameras in France as well, and some in Germany, but you could see the rise in the light curve, and it's perfectly aligned across a huge number of cameras, and you can tell, yeah, that was a common event that they all saw. I would say kind of determining that there is a bright event is maybe not that hard, because we do have still detections with the fireball detector. It's taking it a step further, taking it a step saying, okay, let's do something with this data and let's create some trajectory that kind of makes sense, that's not going to be completely out of whack, and also what if it's an interesting object, then the filters might reject it. Dave, you have your hand up, so please, I want to hear your thoughts.
Yeah, sure. One of the things I'm trying to do, Pete, is I don't want to detect the fireball the next morning. I want the data to start flowing into Dennis within 3 or 4 minutes. You know, I'm setting stretch targets here, but that's what I really want. I wanted the thing to hit the ground and just have the data within 3 or 4 minutes.
That's right. Ideally, you know, the perfect world is that, oh, we observe a fireball and then we get the wind model within 10 minutes and there's a drone that flies
So
out.
one easy way to do that is to go to the American Meteor Society website and take all their detections and immediately verify those against where the GMN is pointing. At least you don't pick up all the fireballs because they don't have detections often deep in the night and so on. But
yeah, that works.
yeah.
That works now, but the American Meteor Society website is going to be radically changed and moved to new servers. So, you know, I just had a conversation about that last week. So the putting your detection, you know, your source of trigger or whatever on an external website that is in flux is probably not the best idea.
It's a source of data, yeah, once it stabilizes again, that could definitely be utilized. But there needs to be also an internal mechanism that needs to be done and developed. But currently, we need to probably put out a vision and then have some talented people like Dave and others work on integration. I think, Dave, you've done it regionally for your network, right? You already have a working system, but it's very specific what you're doing, right?
Yeah, it's I don't know if I'm having internet problems or not, but other people are freezing. I hope I'm okay. Yeah, it's worked once and it's not worked lots and lots of times. So that's kind of where I am in my development pathway. You know, I'm completely frank about these things. I think I've got the genesis of an idea that could work. I just need to work out what the right coefficients are for rejecting and accepting. But I think what I've brought that's novel is using the dictionary of successful Meteor reductions that's already in the GMN database as a clue to, is this real? Or is this really an object we're interested in, or is it just like lightning aircraft to the sun coming up, you know, that kind of thing?
Yeah, that's a good idea. It's basically saying like, can these two cameras form a trajectory, right? And then that's a okay. Yeah, that's pretty simple. It just means that their fields of view overlap, right? That makes sense. For fireballs, that can be a bit different because phanometeors mostly end at or are at around 100 kilometers height, but fireballs can go down to about 30. So the overlap is a bit different, but should be good enough. Derek, go ahead.
So I was thinking probably along similar lines. I mean, I talked to the DFN people. The DFN camera network is optimized for fireball collection. GMN has different aims, of which one is sort of fireball detection, but it has other aims. It wants to capture finer, smaller meteors. And I don't think you should change the aims of GMN. I think GMN works fantastically, but maybe a collaboration between two Meteor networks will give you more information, because I don't think what you're saying about the sort of lower altitude that the all-sky cameras work at will give you better overall fireball detection. So maybe that's your starting point for a fireball, because I know from my perspective here, I'm in Australia as well. The first time I find out about a fireball is when I get a call from Hadrian say, you know, here's this fireball we've picked up in a couple of DFN cameras. Have you picked up anything in the GMN cameras? So I don't know, you know, maybe we're asking too much of GMN.
Yeah, so one thing that it would be, you know, a good idea to do, but that would have to be done on a regional network level, but also on a kind of like, I can't really make decisions for camera operators. But for example, you know, giving Hadrian access to Event Monitor for kind of an approved set of cameras would work well, right? For to give for that kind of collaboration. But that's something that should be worked out on a regional level, because so I already know if, for example, if I was to do this for give someone from Freepon access to any cameras in France, I mean, there would be a World War III, right? That that can't happen, right?
Yeah,
That's why I'm just kind of leaving it up to local operators to to figure out what's going on.
Yeah. I think I would commend that. I think that's the right. And if you look at Mark and UK Mon and the number of camera networks there are there, is there are other complications when you go to other sites. So I think probably leaving it to individual coordinators, is probably the right direction, I think. Anyway.
Yep, that's
There's
that.
also the
Yeah,
there's
sorry.
also the possibility to use the light curve as your fireball detector, because many of the really big objects have sort of this rapid increase around 84 kilometers and then settle because you ran into saturation.
That's
and
definitely
then for a
something.
while, and so there's a pattern to that, and that may also be the
So I mentioned that that's what Damir did for CX1, how he showed that we have it on 100 cameras. It's just the light curve, not necessarily the whole thing. And that could be fantastically used for correlation. And we can say, yeah, we have it on, let's say, at least 3 cameras, and they also correlated with a fireball detection, which the fireball detector did. And they say, yep, pull the data, save it, and notify it. Notify someone. That's it. Dave, go ahead.
Yeah, I've tried the light curve thing, and it's really good at finding lots of cameras that saw the same event. But unfortunately, what it doesn't do is tell me that same event in fact actually was a meteor or a meteorite. So I get the same lightning flash, I get the same aircraft, I get the same whatever, but I've just got lots and lots of things that aren't meteors and meteorites. So it's really cool, but it doesn't quite get me there.
And if we were to include the condition that it has like a fireball detection, now one thing what the server should be doing, in my opinion, is doing a very rudimentary trajectory solution. Something that is wide open and can say it's here somewhere and it could be a decent fireball. That would constrain definitely many false positives, right?
Yeah, well, that's what I'm doing by using existing solutions to guide it. If it doesn't fit into an existing solution, it's probably not real, and that's the best clue I've got at the moment. But having light curves that were objects that we know about, and trying to do a match between the object we don't know and see, does it look like a credible light curve? That might be what I need just to push me over the edge to get something that's a little less likely to flood my own server with the heaps and heaps of false detections, which is what I don't want to do to the network.
Yeah, yeah, absolutely. So that's literally my concern, is that sometimes when during the full moon and fast clouds, the fireball detector is very eager to detect things, and before any kind of further integration and the server being swamped, the fireball detector as such needs to be a bit refined and improved before we move it into that direction. But that's something that could be explored. It's just, how can I put it? From my current perspective, let's say if I want to develop this and provide infrastructure, I currently don't have any incentives. First of all, if I do this, this fireball stuff always gets me in trouble and there's always issues. So that's one. Second of all, that's not really the main focus of my research, right? And third of all, infrastructure costs money and, well, time and money to maintain and support. So if these incentives are not set, then I think we'll have to rely on the work of people like Dave and others who are willing to support this project like that. It's just something I would like to kind of put it out there, and just to kind of maybe people understand why we don't. The fireball side of it is maybe not as developed as some would want. So yeah. any more questions or any other topics maybe that people are interested in?
There's a good question in the chat, Dennis.
Sorry, is it from Will? Is the last one?
Yeah, was it? Sorry, yeah, I'm very intrigued about sort of entry mass calculations, but mass of meteoritic material landing, on for finding. And I just wondered what your feelings were about the accuracy of this. I hear things like, people saying, well, at the end of the day, we didn't find anything, but it was only 20 grams or something that was planned to land. And my gut feeling is that, to be honest, the mass is probably much higher than what people theoretically say it's going to be. And I just wondered, say from the recent find in Germany, with the mass found there, what was the sort of potential calculated mass that was looked at falling, landing in the strewn field, and then statistical nature of the few bits which were found regarding the terrain and how much was potentially not found, if you see what I mean.
So comment I can quickly say, but I'm going to refer Peter to this because he knows more about this particular event, is that it all depends on the quality of data you have. So one good thing about the GMN cameras is that if they observe the end of the fireball, it means it was very close. They can track the rock until the end of ablation, all the way down to like 2.5 kilometers a second. And that gives you a really good way to measure what we call a dynamic mass. I did talk about this last year in the workshop, and I showed the tools how to use them. And you can get a really good idea to maybe within like a factor of 2 what the final mass is. And it is, if I measure 50 grams, it can't be 10 kilograms, right? It's probably between, let's say, 10 and 50. Sorry, like what did I say? If I measure 20, it's probably between like 10 and 50, right? It depends on a few other things. However, if you don't have the end that well measured, we usually use some empirical ways to investigate what the final mass is. But for this particular event, Peter Janskens might have more comments about this, because as far as I know, the checks have measured the potential the mass of the final fragment. So Peter, do you have some comments about that?
I don't have any numbers yet, because this is sort of part of the follow-up. I mean, we want to make as good an estimate of, how big this thing originally was, based on infrasound, based on cosmic radionuclides, based on the albedo of the object when it was seen in space, all those things. And then we want to relate that to what was actually found on the ground and what the Pavel and his team find from how the meteoroids are ablating. And so let's wait for that. In the case of TC3, we calculated that 39 kilos of an object that was 6 by 2.5 by 4 meters or so survived. So it was a tiny, tiny fraction, of which about 11 kilos were found. So these fragile objects, this one definitely was as well, there is not that much material that ultimately makes it to the ground. So at the moment, we have a little over 100 meteorites that we know of that were found, and a little over a kilo in mass. So the object was definitely more than a kilo. So again, probably a small fraction of what came in made it to the ground in this case.
I believe that the initial estimates, I don't know if that's what they published, but I think they said that the largest mass, the main mass, is maybe around 300 grams. And the main mass that the Polish team has found has been very close.
Yeah, the Polish team found 170 grams. There was another observer who found a 225 grams, I think, mass.
Yeah.
But Pavel did some work. He published that already on the website, where he showed where he expected fragments of certain mass to have fallen. And so who knows? Maybe that some of those larger fragments will be found after all.
Yeah. One thing to note is also why video has a much better advantage if you catch the fireball over some photographic all sky, for example, like BFN, is that you can track individual fragments at the end. You can measure their mass distribution, and you can say, yes, there's been like a, let's say, one 200-gram object, and there's been 200 grams, and there's been 50 grams approximately. And then you can kind of coordinate your search region. But mostly the issue is in those first days of search, there's so much uncertainty in terms of, for example, winds. Usually waiting for the wind model takes a couple of days. And the usual strategy is, and that's also something Peter can speak to, is identify big fragmentation points on the fireball's trajectory and then drop little meteorites, tens of grams. And because there are way many more of them, we can talk tens or hundreds of those. And then if you find one, you have a much greater chance that you know you're on the right trail. And that way you can kind of calibrate everything else. So that's something that we've done for CX1 when it happened.
So my strategy is always to bring as many people to the field as we can, but bring a school class of children along, but you have to also educate them that they know what they're looking for, and that's something that, this was very frustrating in the case of the Berlin thing, that even I did not expect meteorites to look like this. So, yeah. I mean, I was looking. I'm sure that if I'd seen this thing on the ground, I might have just walked by it.
Yeah, no, I absolutely agree. So for people who are not aware, I think, Peter, you found almost every single meteorite from an asteroid that was found before, well, if it landed over ground, except this one here in Canada.
Yes, which is frustrating me mightily, but that's right.
It all landed in Lake Ontario. The big piece is somewhere in there in a vineyard still. So, okay.
And by now buried in, some distance in the ground. Yeah.
Fortunately, who knows? We do have a question for Peter McKellar. So, Peter, go ahead.
Yeah, I was just, we have a problem with bugs around here a bit because the cameras are on public sites. There's always security cameras. I've got one in my own town. I can't get near it at night. It's sort of, everything's locked up. So I'd like to know where the light's coming from. But I'm just wondering, is there any developments from the AI side of things? I remember you made the comment one time, we haven't trained the AI for bugs. And this would help with your data with the amount of surplus false alarms that are being sent up.
We had the exact same question at the first session. So Paul Rogermans has manually filtered so many detections, and we have the data set. But the issue right now is that the student who developed the method, we don't really have the kind of the same way he used to train it, because he kind of did it in multiple steps and just delivered a model. And we don't have the pathway to how he got the model. So we have the data now, and we have the final model. We could retrain it, improve it, but we would have to invest time to get to that pathing. And I don't think it should be too complicated. I think anyone who wants to, if you know a few things about Python, but you're interested in a few things about like, oh, let's do a bit of machine learning. It's literally like 100 lines of code, and you could probably do it.
No, I don't think so.
Yeah, go ahead.
Oh, thank you. Yeah, thank you. Time is always the problem, isn't it?
Yeah, that's how it is. Lexi, go ahead.
Hey, I'm glad that question was asked because we have the same thing with birds, especially in the regional sites. And it's really nice that we get the trees. I actually quite like that there's a tree in the bottom of some of the images, because Dave's made the day mode version. I'm not sure if actually, Dave, that's something that's shared widely, but day mode is quite cool because it has the outreach potential of sharing, the fact that trees in infrared look quite different. The leaves are pink. A lot of people think it's cherry blossoms. Anyway, back to the birds. Yeah, we have a big thing with birds. So the maximum projection image, whatever it's called, is you get a lot of like wavy lines with birds on there. Is there a way that you can filter out detections that have frames that go over a certain number of seconds. So I only had a brief look at the config file, but I think it's like there's a minimum number of frames for a Meteor. Can you cut like a ceiling and then filter out at least detections that would be over 10 or 20 seconds? Because I mean, I'm not sure actually what the maximum trail of a Meteor would be, but you know, if there's a bird that's wandering around in the field for that long, at least kind of splitting up the detections in that way. Haven't had time to really look at the code properly, given all the other things I've been doing. But I was wondering, if there's a max limit on the frame detections.
So before we employed the machine learning filter, we used a set of empirical filters, which we removed now that we have the machine learning filter. And the truth is that the only filter we have really is on the angular speed of the detection. And that really sets the difference between meteors and satellites. All satellites are less than about 2 degrees a second, and all meteors are mostly faster than that. But in terms of birds, there is more information that can be used to filter them out, and that is the image information that the machine learning filter is supposed to do. But again, as I said, the first iteration wasn't really trained on a lot of like bugs and birds. It was trained on a lot of clouds and planes, and does a pretty good job with those. But now that we have that data set, we just have to retrain the machine learning filter. That is the best way to do it. Instead of introducing a lot of some kind of empirical things, because you can have an earth raiser and the fireball lasts 30 seconds, and we don't want to lose those, right?
I guess it's like it's a bit longer, but then like you said, it does have a different pattern that shows up, which is quite cool, because then you actually, if you made a pixel region of a certain size, it's got quite a lot of variation between the bird's body and the wings, which are usually a bit fainter. So having like a filter that could detect that variation, I don't know what it would look like, but I think personally I would actually like to see not just birds filtered out, but that you could make a global bird network. Dave's sick of me talking about this, but I think in terms of outreach for schools, the data about birds is something that could be communicated. It's not really a priority, but maybe if someone's got too much time on their hands. But yeah, I think I did look at, it's like the maximum intensity pixel. That's not the word for it, but if that filter could be bigger, and then you could have, I don't know, don't have the time, but that's awesome to know. And so if anyone does discover that, I'd love to know. So I'll keep an eye out, but feel free to contact me about birds.
People to give talks. I actually contacted one person who is a professor of ornithology somewhere in the US who installed a camera. But I don't think his camera is running yet. And asked him, do you have any plans to observe birds and bird migrations? He says yes, but right now the camera is still not working. So it's definitely something in the making. And as I said before, the data is there. We just need to find someone to use the data and analyze it, and kind of really. So Pete Ashman has his hand up. So you might know something about this.
Well, I can speculate, of course. One comment about the problem with insects. We have 2 cameras on a rooftop with nearby parking lot lights. It's a 3-story building, and the lights attract insects and the insects attract birds. So as an experiment, we installed an electronic insect repeller. So it basically generates noise, high frequency noise. It's got 3 different settings. And on the high setting, people can actually hear it. So you don't use that setting, inside your house. Well, it actually worked to some extent. There are fewer insects now in the camera images. And the ones that are there, of course, are further away in the field of view, because they're further away from the sound. And of course, the insects attract birds, so therefore there are more birds in the cameras as well. But if you're really interested in birds, then you should be running something called Bird Pie. Bird Pie runs on a Pi and it uses a microphone that automatically classifies bird songs. And in fact, will produce a nice little table of how many birds and different types of birds you got that day. And it will record these segments of sound so that you can play them back. It turned out that we had an awful lot of owls in our neighborhood, but they weren't owls at all. They were dogs barking. So I had to remove all of those types of birds. Anyway, it's called Bird Pie. It's widely used in the US, especially by people who are bird watchers. I just throw that out there. It's another good way of using an old Raspberry Pi. So, for what it's worth.
It's a great
That-
suggestion.
That's awesome to know. Yeah, I think I'm just going to post one of the cameras that we've got if anyone wanted to have a look at the one that has lots of birds in particular. You can have a look at another time, but I think I'm wondering if the radiants that go on the solar longitude, if that's actually is that actually plotting some of the bird movement if it's detected? I haven't asked anyone that yet.
Yeah, that's definitely bird movement. Yep. That's
Yeah, it's quite a fascinating way, I guess, to look at bird movement through the sky, plotting it on solar longitude. I mean, perhaps that's something they already do, but yeah, thank you for letting me indulge in birds for the moment. But it's great to hear, yeah, other people have been thinking about this as well. So
yeah, so this camera, I can tell you right away because of the high sporadic rate, is actually rejected by a couple of procedures because it detects that there are way too many sporadics from an unassigned meteor shower, and it's going to say, I want nothing to do with it. And that's usually an indication that it detects a lot of bugs and birds. So yeah, that definitely needs to be addressed because this camera is not currently producing a lot of useful data, at least not for flux. It still tries to solve trajectories with this, but it's unsuccessful, definitely. Perhaps something that maybe a lot of people in the GMN don't know is that until GMN came along, and maybe a few years before that, the dominant way that amateurs operated meteor cameras was that they manually filtered all detections using the software like the bin viewer through what's called a confirmation process. And there are people in Europe that are still doing this, to manually go through and check every single detection. And that's something that I've been doing when I got involved in meteors. And you would have a cloudy night with 2,000 detections with 3 real meteors, and everything else is just clouds. It was an absolute nightmare. So let's say that I wrote a lot of this code as kind of some sort of a vent to kind of say, okay, I can do better than this, and that's where we are now, right?
I actually saw that. I was playing around with bin viewer, and I saw that confirmation process, and I went to that, and I thought this must be the way they used to do it.
Yes, in the olden days. Fortunately, today we can focus on actually doing important things and not wasting our time on clicking yes or no.
But it was actually fun to do. That's why people were doing it.
It's
It
true.
was actually, I had a hard time convincing people to not do that because in camps we really didn't need it.
Yeah.
You know, you get a lot of false detections, but in the triangulation process, you weed out also a lot out because it's just not triangulating.
Yeah. Yeah.
But it's fun to do. And if you're a meteor observer and you grew up like me on a reclining lawn chair, you know, plotting meteors, then it's, you know, it's lovely.
Yeah, I used to spend an hour a day. Fortunately, that hour is now spent writing papers and analyzing showers. It can be relaxing. I can definitely say that.
I thought you get AI to write the papers.
That's right. No, we got the AI to do the boring stuff. paper writing can be fun. Okay. Do we have any last points? I would actually personally like to wrap up the meeting pretty soon, but I will gonna leave it open and you guys can chat. Here it's getting really late, so I might duck out soon. So it's kind of a last call from my end.
Just a reflection from me, just listening to the discussion. I think there are different camera networks out there, and we talked a bit about cosmic ray bursts, which is another end of the spectrum of what can be captured. I think we need to have a bit of a vision as to where GMN is going alongside other networks and other technologies. And I tip my hat to Dennis and Mark. The amount of time we must put into this, just talking to people, etc., is incredible. But we need to understand, seeing fantastic work that Lex is doing in New Zealand, and I can see the same thing happening in Victoria. We're going to have 5 times as many cameras, in 10 years. So someone needs to take a long-term view and a strategic direction of where it's going, and so that Dennis has still got some time to do his fantastic research and stuff. So so that would be my reflection on it. So yeah. But I don't think we necessarily want GMN to do everything. It's got a quite a focused mission, and I think it's doing its job fairly well. We can fine tune it, but we got to say, well, there are other networks that are operating alongside it. Yep.
Yeah, absolutely. That's a great question. So I did touch on a few of these things in the speech at the beginning of the first session, and that is that the way the network is envisioned in the software is that it gives you it's based on the core values of free software, the free software movement. That's something that's, the ideas of people like Richard Stallman and a couple of other crazy hobos, so at least that's how they look like. And the whole idea is that, what you get is software that's both free, as in free speech, and free beer, that you have full freedom to do whatever you want with it. And if there is another vision that people want to take this and run with it, that is definitely this can be going in that direction. And I think the reason why there were so many kind of regional efforts that are possible is because of the people can just take it and run with it without any need for control from my end. Whatever's happening, I'm just happy that it's happening. And sometimes I don't want to have nothing to do with it because it's just completely outside of whatever I'm paid to do and what I have time for. But I fully support all efforts, and that's the whole idea of the network. So it's I would also say it's kind of up to you to figure out what you want to do with it, and then just kind of take it and go with it. And if there's something I can do to support it, great. So Lexi, go ahead.
Hey, I just wanted to share again the outreach meetings that Redim and I are hoping to have. So Redim and I talked about a date in March, the 25th in March, potentially to have a public online meeting. We haven't set a time or advertised it, so not sure if that will still go ahead. I think Redim's going away in April, so it would be nice to have it then instead of delaying it. But it would be awesome in the next few weeks. Again, if there's people that are willing to share the outreach stories and sort of connect online, please, I'll just post my email in chat. Please reach out to me, and I'll try and post it on the forums as well, and we'll try and work out a date. So I just wanted to flag that. And yeah, thanks again, Dennis, for all your work with this. It's been fantastic fun.
Oh, well, no, thank you. I mean, it would be nothing without you guys taking charge on the outreach thing, which is absolutely amazing. One thing also that I want to say is that you did a lot of hard work for writing the project and report for what is relatively a small amount of money. for it's only $4,000, which we kickstarted the outreach program by it was so first it's the end of the day, my brain is not working anymore. We applied to one company who was willing to donate a certain sum of money to help kickstart the outreach program. And then once the war that happened 2 years ago happened, they dropped everything and they just donated everything there. And then we were kind of already assembled people, put everything together, and we were left kind of holding the bag. And fortunately, one of the GMN members was very kind and said, I'm going to pick it up, and donated 10,000 US to keep the outreach program going. And that's where we are right now, which is this kind of kind donation from the member. And we do still have, that's something that I kind of reluctantly advertise because I don't really want to ask money, but we do have the Patreon page, and through the Patreon page we did finance some cameras for outreach. We did finance, I think, some Radins travel and a few other things. Right now, the sums are enough to keep some server costs running, but perhaps if the outreach program was to really fully flourish, or at least kind of maintain itself at a certain level, that's something we could look into. But kind of any ideas of kind of subscriptions or anything like that, I really want to stay out of it. Usually the way it works is I kind of take the money out of the account, I have to pay taxes on it, and then I just send it via PayPal to other people. To keep those things funded. We did think about other ways of doing it, involving the university in it and trying to kind of make it more official, et cetera, but just the moment you approach an institution, the amount of red tape increases exponentially, and then you say, oh, there's a thing like overhead, and overhead is we take 50% and give you nothing in return. Just like, okay, we're going to do this some other way. So, okay, Pete Eschman, you have a comment.
Just one comment. One of the things we did when we were pricing cameras, building them locally, and basically what we tried to do is build in a small amount, like $25 for labor, but the money went into a pool to help us purchase more equipment. It never went into anybody's pocket. The other thing we did is that we built in like a $20 per camera donation that we ended up sending to GMN. So I could suggest that other people consider this. It may or may not, you might not find it suitable, but it was a way to generate a small amount of money, send it to GMN, and generate a small amount of money that we could use to buy parts to build the next set of cameras. So I'll just throw it out there. It may work for you, it may not, but it might be worth considering.
That's a great suggestion. One thing we could set up potentially is, let's say there's a financial assistance required, and let's say someone wants to install a camera somewhere, can't afford it, et cetera, or there's some sort of a support. The GMN could have some form of a kind of a community grants where you would just kind of write like, this is why I kind of need the money, very short, this is why I want to install the camera, and we post it on the group, and then we can kind of open up the donations and say like, well, if people want to give a few dollars here or there, we can help this person get the camera or whatever. But as long as there's a kind of a clear narrative of why that's getting funded and what's going on, that's definitely something that we could do, right? It's a way going forward. I'm not saying that I necessarily want to manage it. If you guys want to do it from your end, perfect. That's even less work for me, and I don't want to navigate the international money transfers. That's a nightmare. But just putting it out there, I think we have members who are willing and want to help. and it's a good way of doing it and building up if money is tight. Yeah, good. Well, thank you again. I think this is where my participation is gonna end for this year's meeting. Thank you again all for coming. It was incredible, and hopefully next year we can at least match this year's level of quality. Get a few more invited speakers again, just to see what, like why are you inviting this network and what are these scientists even doing with this data. And get more people involved and have a more amazing discussions. And yeah, that's it. Well, thank you all, and see you next year, if not sooner.
Thank you all.
Thank you, Dennis. Particular thanks to you, Dennis.
Yeah.
You go get time to go to bed. Thank you.
It is time to go to bed. Thank you. Bye.
Thanks very
Thanks,
much.
Dennis.
Bye.
Dave, do you